Ένα, δύο, τρία, τέσσερα, πέντε, έξι, τεστ. Ένα, δύο, ένα, δύο, τρία, τεστ. Ένα, δύο, τρία, τεστ. Ένα, δύο.
Hello, everyone. I would like to welcome you to the first workshop of the Greek Supersite. We're going to have some welcoming addresses first. I would like to ask Mr. Michalis Kalogiannakis to proceed here to give his address. Thank you.
Sorry for my Greek language, because I didn't know that here. I believe that here the audience is only Greek. Αγαπητές κύριοι, αγαπητοί κύριοι, ως πρόεδρος του Πανελληνίου Συλλόγου Διπλωματούχων Γραμματογράφων Μηχανικών, σας καλωσορίζω και εγώ στην πρώτη ημερίδα του ελληνικού Supersite του GSNL. Είναι πολύ σημαντικό δημόσιοι φορείς όπως ο ΑΣΠ να συμμετέχουν σε διεθνείς πρωτοβουλίες όπως αυτή. Η παρατήρηση γης είναι αρκετά σημαντική για τη διαφύλαξη της ποιότητας ζωής των πολιτών αυτού του πλανήτη, ενώ είναι αναγκαίο ώστε να προκύψουν χρήσιμα συμπεράσματα για τις αλλαγές στο φυσικό περιβάλλον και την ανάπτυξη των πόλεων και όχι μόνο. Στη χώρα μας συγκεκριμένα, η οποία έχει έντονη σεισμική δραστηριότητα, η παρατήρηση γης πρέπει να είναι προτεραιότητα. Δεν πρέπει να ξεχνάμε ότι είναι η πρώτη χώρα σε σεισμικότητα στην Ευρώπη και έκτη σε όλο τον κόσμο. Η αντισεισμική προστασία και ο σχεδιασμός για την εφαρμογή των απαιτούμενων μέτρων είναι σύνθετο ζήτημα και απαιτεί διεπιστημονική προσέγγιση και συνεργασία επιστημόνων με εξειδίκευση στη γεωλογία, σεισμολογία, στη γεωφυσική και στην αντισεισμική τεχνολογία. Τελευταία θα αναφέρω τη γεωδεσία και τη τηλεεπισκόπηση, γενικότερα, τη τοπογραφική με επιστήμη, η οποία αποτελεί κρίσιμη πτυχή της διεπιστημονικής προσέγγισης, διότι είναι υπεύθυνη για την πληρέστερη περιγραφή της γης και των αλλαγών που συντελούνται. Τα τεχνολογικά μέσα έχουν εξελιχθεί αρκετά και μας επιτρέπουν πλέον η παρατήρηση της γης να γίνεται με πληρέστερο τρόπο. Από τη γη με επιτόπιες μεθόδους, από τον αέρα μέσω δορυφόρων αλλά και drones για μικρότερης κλίμακας περιοχές ενδιαφέροντος, αλλά και τη θάλασσα με μεθόδους βυθομετρίας. Επειδή οι παρουσιάσεις που ακολουθούν τις αναμένω και εγώ με πολύ ενδιαφέρον, θα κλείσω σε αυτό το σημείο το χαιρετισμό μου, συγχαίροντας τον ΟΑΣΠ για την ενεργή συμμετοχή στην πρωτοβουλία αυτή και θέλω να ευχηθώ καλή αρχή και καλή επιτυχία στις εργασίες της ημερίδας αυτής.
Ευχαριστούμε πολύ, κύριε Καλογιannakis. I will follow with the speech from Mrs. Professor Chrysi Potsiou. She couldn't make it to be here with us today. So Mrs. Potsiou is the chair of the Fédération Internationale de Géométrie. On behalf of the International Federation of Surveyors, I welcome the first annual Greek Supersite workshop in Athens, and I confirm the interest of surveyors to share experience gained from this project among all land professionals working in the field of good governance and citizen safety in densely urbanized areas. The Group on Earth Observation, the International Federation of Surveyors, and all other international sister organizations have common interests in addressing the global mega topics and very often work in parallel for the benefit of the society in the fields of land management, positioning and measurement, engineering surveys, construction economics and management, spatial planning and development, and many other. The Greek territory suffers from continuous seismic activity. Even during the recent years, there are several examples of the Parinth earthquake and also the frequent earthquake events happening in the Ionian Islands, the Corinth Rift, among others. The Greek Supersite is of the great interest for further evaluation from the experts in order to facilitate the developments and improve sea protection. Experience derived from this project will be of value for other regions as well. Personally, I would like to congratulate the core research team for their initiative and wish you all to have fruitful deliberations. We welcome you to present your achievements and we look forward to promoting your results and sharing your experience in this field within our global surveying community in our coming events. Professor Chrysi Potsiou. So I would like to ask Dr. Salvi to start with his presentation. Yes, the middle one is the pointer.
Okay.
Just keep it close to this.
Like this?
Yeah, okay. It doesn't work.
Okay. Thank you. Can you hear me?
Oh, you have to press.
So it's a great pleasure to be here, and I thank Alexandros
for inviting me. I'm very happy that Greece now has a Supersite. And my duty today is to explain to you what the Supersite initiative is, what being a Supersite means for you, for the community, and also for people who are not here but will be part of the community in the future. Yes, it's the one. Okay, the below. Okay, so the Supersite initiative is an initiative in GEO, which is a group on Earth observation, which is an intergovernmental group of governments and associations and organizations whose main scope is to improve the international collaboration for the sharing data, knowledge, and activities in environmental monitoring. GEO is a framework. There is little, let's say, there is no funding in GEO other than the Secretary of GEO. But GEO is a framework under which projects and initiatives can be generated and proposed by bottom-up from the scientists or top-down from governments. GEO was established in 2010 at the G7 meeting, and it was renewed. I mean, the support to GEO was renewed at the 2015 meeting of the G7 science ministers. So GEO is born out of science, but it's not limited to science because also private companies now are becoming part of GEO. It's a big organization. Now this number has increased. So there are many countries part of GEO, and they have delegates, and these delegates should stimulate participation of the scientific communities, the local national scientific communities to initiatives of GEO. There are 8 benefit areas, and disaster resilience is the area in which the Geohazard Supersite initiative is placed. So let's get into detail. The Geohazard Supersite and Natural Laboratory Initiative is what it is. It's a partnership. So there are groups of community of people which has the main objective to improve through an open science approach, which means open dissemination of data, knowledge, tools, and whatever is needed to make science, to improve these scientific efforts on specific seismic and volcanic areas. Now we're also moving to different hazards, but so far it's been only seismic and volcanic areas, which are called supersites or natural laboratories, to provide scientific information which should hopefully be useful for disaster risk reduction. This is the partnership. Scientific community. Of course, there should be more logos here, also from this room, but this is the main bodies. We will update these slides. And the in situ data providers, those who have ground network to measure these parameters of these phenomena, and the satellite data providers. All these agencies are grouped under one main organization, which is called CEOS, the Committee on Earth Observation Satellites. So what is the role of scientists in disaster risk reduction? Of course, it's understanding the hazards and the risk, the assessment of hazard and risk, but it's also to ensure proper and timely communication of this information to disaster managers, to decision makers. And this has been recognized in the 10-year UN conference on disaster risk reduction, which was held in Sendai in 2015. It's a conference which is held every 10 years. And this, in this last conference, they developed the Sendai framework, which is, let's say, a document in which science has been put in as one of the priorities, because knowledge of the hazards is a very important part for improving the disaster risk reduction. So the end of the story is scientists should study this phenomena, but they should also provide or take care that this information reaches the final users in a timely way, because otherwise it stays in publications and is not so effective. And this is one of our goals. We have permanent supersite and event supersites, but I will not discuss the event supersite. The permanent supersites we have in the initiative now are 8, thanks to Enceladus supersite. And we will have this year maybe 3 for sure. The San Andreas Fault Natural Laboratory will be a reality, and maybe 2 other supersites from Chile and Democratic Republic of Congo. Sorry. All these supersites are managed, let's say, coordinated by researchers who are belong to institutions who have a mandate for providing information to disaster managers or decision makers or governments in different countries, like INGV, USGS, and ITSAC, and COERI for Turkey, and so on. So the idea is this coordination, which is carried out by these institutes, is taking advantage of the larger international community doing scientific investigations in these areas to improve the information which is provided to the users, decision makers. So we have 4 main lines of action. First one is scientific collaboration. We want to improve the collaboration, and this is done through improving data access, but also improving research capacities. In some countries, especially developing countries, this is a very important part. In some other countries, maybe it's only a matter of having better data access. Then we want to use innovative technologies and processes to improve this collaboration and the knowledge sharing and the capacity building, again, for developing countries mostly. And then we need to ensure that this information in the end benefits the disaster risk management at the local scale, the national scale. So that's why we need a link between the coordinator and the decision makers at the national scale. And of course, this is done through some kind of in-kind contribution, but also through funding. The funding is not something we take care at central level, at the initiative level, but it's something which is left to the supersite to attract. So we will see these items one at a time. Scientific collaboration. Okay, these are the conditions for a supersite to be such. I mean, we need to share data, knowledge, and resources openly. There will be there will be a data policy. There could be limitations, but the rationale here, also in GEO, is to have open access to data and knowledge, open science. Then we are already at this moment developing virtual collaborative platform, virtual research environment like Everest. We are ESA is contributing the GeoHazard exploitation platform, JEP, which is a tool. I think Fabrizio will show the JEP later on. And so we want to improve the way that these data are shared and the way that collaboration is done. Then another pillar of the supersite is that we need not just the data, but also the results of your science to be shared. Normally, people publish the results, and the publications sometimes they may contain data, but normally they don't contain the models on the results in a digital form, reusable digital form. This is not possible for supersites because we want to make this very open sharing of knowledge. So also your results after publication should be shared and made available. And of course, this is something that in which the role of a Supersite coordinator is very important. So the stimulation of discussion and knowledge transfer and capacity building, and in general, collaboration. Data access is a very delicate part, and it's the reason that this initiative was started at the beginning. So the sharing of data and also results, this is done, of course, respecting the intellectual property rights of the owners through normal means. Then the data should be made accessible through digital platforms. We don't want people to call, can I have this file or so on. This could be really open, should be really open and accessible. And there are different platforms already available for this or being developed. And GEOS is the Global Earth Observation System of Systems, which is, again, another platform in which all data from GEO, from all societal benefit areas, should be discoverable. So from the disaster resilience, but also for the energy, earth, and carbon, environment, and so on, should also be accessible through the GEOS platform, which is being developed by the European Space Agency. The coordinator are, again, let's say, the sentinels to which we refer to ensure that these conditions are respected. Okay, and we will also like that for each Supersite, a Supersite is like a place in which scientists, but also university students, for instance, go and find all information related to that area. So should give access to literature, in an open way. We have to devise a way, but you know, people who have not possibility to pay for articles should be able to find their articles there. So literature, gray literature, which is project literature, and so on. This is an example of the open data portal for the Mount Etna and Vesuvius supersites. And this is a machine-readable portal, so people can query the database using web services and extract the data, and they don't need to interact with anybody. They just have a login, they get the data, and they do their research. And this is a similar one for the Iceland Supersite. And they have many volcanoes mapped, and for each volcano, they have lots of data made available to scientists. Of course, it's not fully open. I mean, you need a registration process, you need a login. And when you log in, I mean, the login is useful to track the use of this data. So, but if you ask to be registered and to get a password and a username, they cannot be, you cannot be forbidden to use it if you are a scientist. I've been asked by my colleague Massimo Cocco to put a few lines on EPOS and the supersites, because sometimes there are some misunderstandings. EPOS is part of GEO, is a supporting organization, participating, they call it, but in fact it's supporting. And EPOS, which is the European Plate Observing System, as you know, it's part of GEO, especially because it's supporting the European supersites. And why is it so? Because the European supersites have this duty, let's say, to share data. And EPOS is a research data infrastructure. So it's exactly the same thing. What the supersites are in GEO, in EPOS, is they are what is called thematic core services, which are, let's say, entities in which the data belonging to the supersite are provided to the scientific community through EPOS. So EPOS is providing, let's say, an infrastructure, will provide, because EPOS is under development, will provide an infrastructure to distribute the supersite data. And EPOS is also important in this context because EPOS is a pan-European organization. So it means that EPOS negotiates with local governments, also with the Greek government, to get funding for the local initiative. So the supersite in the future could be part of this framework and could get also funded. I mean, some activities, the data distribution activities, could get funded through this mechanism. That's why I think the community here should work closely. I mean, he thinks that should work closely with EPOS. So the resources, as I said, we don't have funding. I mean, I'm a voluntary, I do this work aside of my work at NGV. But we expect that in each Supersite, the scientists, the community is getting funded through the normal means. I mean, they will write projects and they will try to get institutional funding to support, for instance, a website development or research on these data. And of course, the fact that there is a Supersite is providing a way to leverage on these funding opportunities. At least in most countries, it's like that. However, we should not link the funding with the success of the Supersite, because if you do not get funded, doesn't mean that the Supersite has not a reason to exist. Supersite has a reason to exist because it is a way by which scientists can benefit the society at large, let's say. Not just Greek scientists, but also international scientists. So we do expect the in-kind contributions, of course, with limitations, depends on the possibilities of each other. Supersite and disaster risk management. The national risk managers need to receive a good scientific support. This is clear, and it's also in the Sendai framework for both prevention activities, hazard assessment, but also for response during earthquakes or volcanic eruptions. And we said already that the Supersite coordinator is the one that, well, we didn't say it, but the Supersite coordinator is the one, is the main interface between the users and the scientific community, not just the local scientific community, but the international scientific community. We don't want in a Supersite that scientists from a faraway country is doing specific research during a seismic event, for instance, and then he provides these results directly to some decision makers or to the media, because this is not good. It's not a coordinated way of working. We need consensus in the scientific community, and this is something that we have experienced in Italy many times. And so the idea is that the coordinator of the Supersite is the main interface between the knowledge generated by the scientific community and the support to the decision makers. And the end users also are not just passive, receiving information, but they can also be proactive and saying, okay, we would like to have this specific topic investigated by the scientific community. So this is something that they should do because it has a high priority for them. Now, very briefly, I have an example from the Iceland Supersite in which we will see the exact chain of actions which we would like to see for each Supersite. Of course, this is regarding a response case, but also for prevention. I mean, for hazard assessment, this could be a good example. So this is the Iceland Supersite, many volcanoes, over 30 volcanoes monitored through satellite images, and the data are provided by local scientists and monitoring agencies. In 2014, there was a big eruption. Well, it started as a big eruption in a caldera, which is covered by 800 meters of ice. And you will remember in 2010, there was this Eyjafjallajökull eruption, which lasted several weeks and disrupted completely the air traffic in Europe, and not only in Europe. So and that was caused by interaction with magma and water, like this one. So they fared at the beginning, and the Daily Mirror headline here is focusing on that. This was a doublet of the other eruption. So it was very much concerned, especially in the UK, for a big explosion and ash blocking the air traffic. And so it started a complete, a very detailed analysis, investigation carried out by the Supersite people, the Supersite scientists. And they received lots of data, a lot more data than normally. These are, I think, Cosmos Skymed or TerraSAR-X data, but they received data from all space agencies. And they were able to model, in this case, the interferogram shows this is the main location of the eruption under the ice. The white is the ice, but this dike was rapidly shown to move all the lava coming out from the main caldera outside of the ice. And the several different scientific results were produced by this community of people. And this information was constantly provided to the decision makers, the Iceland Civil Protection. And at the end, a decision was relatively rapidly taken, in which the red alert, which was issued at the start of the eruption, was lowered to orange and then was lowered to normality, because the eruption was not going to be very explosive and there was no risk for high ash columns. This is a typical example in which the data are used to generate new science. Scientific community is coordinated by a local Supersite coordinator, and the information reaches the decision maker, and a very good, important decision is taken, which is saving a lot of money and providing very good benefit to society. I'm finished. This is just the summary of Supersite. We have, I didn't speak too much about the Greek Supersite because I'm sure you. So, but there will be lots of satellite images provided to your Supersite, and we hope to increase also the number of scientists participate in the global initiative, and we hope also that you are able to increase this number, getting more funds for this Supersite. But I want to remind you that there is, we calculate approximately about 6 million euro per year of the in-kind support provided by the partnership. Most of this is satellite images, but a good part is also science, scientific investigations. Thank you, and good luck.
Thank you, Stefano. If there are any questions to Dr. Salvi? Yes, Mr. Papagiannou. Christos, just a minute. Take the microphone. Just say who you are and the organization.
I am Christos Papagiannou. I'm a research director, seismologist at the research unit of OASP at ITSAK in Thessaloniki, where Alexandros is coming from. I have a question. You said twice during your presentation that the data that within any Supersite data should be or shall be or must be free available. And I don't understand how one can guarantee that the data that will be provided will be free available to the National Scientific Committee, or the data which will be produced after the elaboration of primitive data, raw data, will be or must be available. How can you define the word must, the obligation, if there is no financial support for the production of the data?
I understand this. I think the main solution to this will be EPOS in Europe, at least. Of course, as I said, funding, I mean, sustainability is something we want. We don't want a Supersite which is only 2 years or 1 year, and then people say, okay, we don't have funding, we cannot continue. So there must be a way to sustainability, and this is an important part. But they are related. I mean, if we don't show that the Supersite is able to provide open access, there will be no funding coming in. So that's why I talk about in-kind contribution. The beginning is providing open access in kind, and seeing by the external institutions, also the community, European Commission, and also your government possibly, that this is improving the visibility of the area, is having societal benefits, quantifiable societal benefits. And then maybe your government could be convinced to spend more money in funding your ground networks. But of course, every super site is asking the same question. How can we maintain the networks? I can tell you what we do at INGV. I mean, we are paid, our networks are paid without any super sites. So we are obliged by the law to provide this data for free, open. And so there is no necessity for us to have additional funding. The necessity is important when you have additional networks to be deployed, additional investigation, and so on. But this is part of more for research projects rather than stable, sustainable funding. This is not the case everywhere. I understand may not be the case in Greece. So something should be done, and we are, I mean, we can lobby together through GEO. I propose this to USGS. USGS is a big institution, but they don't have much money also there. And so I propose to them, we can write a letter from the Supersite initiative, GEO, saying, asking the USGS director to support the Supersite in Hawaii, because they need to put more money, because there are a lot of scientists worldwide who are interested in this data and so on. So there are different approaches to this. I don't have the recipe, but...
Okay, thank you, Dr. Salvi. So the next presentation is from myself, the Greek Supersite coordinator. First of all, I would like to thank all the Greek Supersite core team. Most of the people are here. I can see them here in the front, and some of them are connected through the Adobe Connect link we have. It has been really a big effort all these years. We had to have a very successful proposal. It was very nice to have through the procedure of the submission, nice cooperation with Dr. Salvi, so that there were some discussions and some things the GeoSAC would like to have from our side. So there has been some updates on the proposal in order to conclude to a successful one. So I'm not going to say a lot about the GSNL initiative. This is already something that Dr. Salvi presented. The main thing I would like to just keep for everybody here is that there should be an open science approach. That means all the information that are available from in situ data should be available to the research community, and this will be further work out with the satellite imagery will be available through the GEO initiative and the GEOS SS. So from our Greek Supersite team, we have 14 green collaborators that have already signed memorandum of understanding with the Earthquake Planning and Protection Organization, the Institute of Engineering, Seismology, Earthquake Engineering, coordinating this. There are 17 international collaborators in the core team, and we have 24 international organizations that provide support letters to this initiative. The region of interest is in central Greece, starting from the eastern side of Attica Peninsula and the Evia Island, and moving to the Ionian Islands on the western side, and then central part of Peloponnese up to the central part of the central Greece. So there are three sub-areas of high tectonic interest. One is the Ionian Islands, As you know, it includes one of the most active regions in Europe, actually the most active as individual rupture zones, the zone between in the Kefalonia Island. Also the Corinth Rift and the Voikoth Rifts. I will provide more details about these three different areas. The area of the Greek supersite has a high societal impact. More than 50% of the population is on this area, since Athens is included in this. And there are millions of visitors per year in this area, especially for cultural heritage and, Delphi and other areas of great interest to tourists. So starting from the Ionian Islands, we have the highest observed seismicity in Europe. We have recently recorded the highest ground acceleration, which was 77% of G, and the epicentral distance of 7 kilometers, which was an earthquake of magnitude 6. And as mentioned before, this area has the highest seismicity in Europe until now. I don't know if things will change with Italy. Recently, we had a lot of earthquakes. So the Corinth Rift is an ideal natural laboratory to investigate the rift deformation mechanisms. Both 5-year GPS and 100 GPS triangulation GPS velocity estimates suggest north-south extension with very high rates. At the Voikoth Rift, we have a strongly thin continental crust below the central section of the northern part with thickness of only 90 to 20 kilometers. And we have a local uplift rate which exceeds 1 millimeter per year. So the research objectives of this initiative is the first two are mostly scientific, and they have to do with mapping the deformation, the stress regime, the time-varying patterns of the seismicity, perform update seismic relocations for the area, and following exploit the available datasets, existing and new datasets. The ones that are very important that follow at the end are the efficient fusing of the acquired Earth and space observations. So it is very important that we manage to use together the in situ observations with the space observation in order to manage to have achieve a disaster risk reduction and quick resilience, which is actually the main idea of this initiative, putting all this data together. So as far as concerns the in situ data, we have broadband and short period seismic stations, accelerometers, campaign and continued GPS data, as well as digital elevation models. All data will be available following the Frascati declaration, that means open access, and that we expect to foster the collaboration between various partners and end users. That will be done similarly to what was presented by Dr. Salvli with an registration module for data that will be available. The Earth observation data, we have already information from different satellite imagery organizations that will be available to the community. That will be optical, multispectral, radar, including also airborne and UAV information. And different technology will be used in order to manage to have fusion and change detection in the area of interest. Copernicus contributing missions with multispectral imagery like Rapid Eye will be available. And we have already received from CNES information for the area of the Greek supersite through the Pleiades satellite. Also, since we expect that the SMEs and industrial organizations to be involved, to have and to support them, to provide this data through different non-disclosure agreements, so that all the available information could be also used by industrial organizations. So there are a number of different activities that we plan, except from the Greek supersite World Wide Web information. You can have a first introductory through the GeoGSNL website, and soon we'll have access to archive data and real-time data, especially when an event will be located in the area. We start with this kickoff meeting today, and welcome all of you. And we are looking forward that more people will be involved in our initiative so that all the data that will be available, we get the best benefit out of them. So our commitment is to provide the data which is available, to provide synthetic consensus reports, and that will move forward to GeoGSNL so that we have a two-way communication with GSNL in order to have the best benefit of not only the in-situ data, but also the satellite imagery, and try to work with other super sites and other international initiatives, and welcome other organizations, both from Greece and other countries, to work with us. As I said, the MOU that is available on the website of the GeoGSNL is a big effort and shows clearly to everybody that we will follow a full open data policy. Thank you. That's all from my side. If there is if there are any questions. No? Yes, Stefano.
The last slide. I have two comments. First, when you call this supersite Greek supersite, you know this is not exactly probably something we should do because there could be other supersite in the future in Greece. So it's better to stay to the Enceladus.
Yeah, that's why we call it Enceladus.
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 And so the other thing is when you speak about synthetic consensus reports, that's perfect. However, we don't need to receive. So GSNL, we don't necessarily need to be involved in your response to emergencies and so on. I think also it's not good for us because it's a national thing. I mean, it's important. We need to show what you are doing in terms of dissemination and outreach, but we don't need to receive the reports you provide to the user because they're probably very delicate stuff that you want to provide to the user. I mean, so I think what you need to do to us, to provide to us, is evidence of what you are doing, maps and so on, and reports, but not exactly the same stuff that you produce for the user in general.
Okay. That's...
At least in Italy, we would not do that. I mean, I would not ask my colleagues to send me the reports they send to the civil protection to send to Geo because it's a direct relationship between two different bodies.
Okay, thank you, Stefano. Any other question? No. Okay, I would like to ask Professor Parcharidis to follow with his presentation.
Okay, good afternoon. My presentation is not a typical scientific presentation, but it's a presentation in which I would like to show you in which areas our group in Harkopia University is focusing. Our prime scientific topic is the SAR interferometry, and we're monitoring land motion. One of the prime areas in Greece is the Corinthian Gulf, which is part of the Greek supersite Enceladus. Okay. So these are the areas where ongoing projects or we have already applied SAR interferometry in the past. For example, starting from Kefalonia Island, we have produced co-seismic interferograms for the earthquake happened in 2014.
Sorry, sorry to interrupt you, sir. We have a request from the people that follow. They don't see your screen. I just wanted to check.
Yes.
Sorry. it's okay. I just want to make sure that.
Sorry.
Sorry.
Are you using Skype?
While using Adobe Connect, it should be okay. I don't know why. Just check from here.
No, I think it's when it goes in full screen mode,
Yes,
this happens.
it happens.
Yeah, go to PowerPoint.
Just a minute.
It's not Adobe Connect problem.
It's we use Adobe Connect that people can see the
Yeah,
presentation.
I don't think it's an Adobe Connect problem. Yeah, but there is another way of showing presentations in PowerPoint. They showed me last week, which is compatible to. Maybe. See? No.
Yes, it's fine.
It's okay?
Yes.
Restart is needed. So we're talking about the co-seismic deformation mapping in the case of the Kefalonia earthquake. And it was really very few days immediately after the event that we published the results, and were very useful to the scientific community in Greece. Actually, we're working in the post-seismic situation in Kefalonia. We have a project. We third-party mission data from RadarSat data, and we're working on this issue. Actually, it's a preliminary result covering the period of the end of 2014 until the end of 2015. A year later, we have the earthquake in Lefkada. So we produce again the co-seismic deformation map and also the post-seismic deformation mapping. Actually, we're working in Katuna fault area. It's in the mainland, in the western part of the mainland of Greece. It's a known fault, active fault in the area, where we apply the SVD algorithm, producing multi-temporal interferometric results. In this project, we have a collaboration with ENS from Paris and the National Kapodistrian University, the Department of Geology. A few years ago, we investigate the delta of Mornos. We know that in the Corinthia Gulf, there are a lot of deltas. So we start working with the delta of Mornos. We apply permanent scatterers interferometry and to see how is the behavior of this delta, because the delta is crossed by an active fault. So we show that there is a strong downlift in the area of the delta and almost stable the area in the mainland. Now we're working in Corinthos city. And we start to work in Corinthos city because according to the notectonic map of the EPO, there are two active faults bordering the city of Corinthos. And we want to see if these two faults are really active as the map is delineated. These are our results. It's not clear that there is a land motion in the area, but we want to investigate more this case. we want to use ERS data to cover all the period of 90s, which is a more long period. The problem in the area is not only to map the hazard, but also to map the results of the hazards on the infrastructures. So we have a lot of infrastructures that are elements at risk. For example, the city of Patras, the exposure are the building stock of the city, where we have urban faults that affect the buildings in the city of Patras. It's clear here in this map that we have different land motion where the active faults cross the city. Another element at risk is the bridge of Rio Andirio, where with the economic support of the ESA, we monitoring the bridge, the behavior of the bridge, which is in a boundary between Corinthian Gulf and Patraikos Gulf. It's a very active area. We apply the permanent scatterers interferometry, and the only elements of the bridge where we can apply this method were the pylons, because the pavement is suspended. So it's a very difficult case, this. And we work on this for 3 or 4 years, if I remember well. We talked with a Gefira company who managed the bridge. They told us that they are very interesting to know about the behavior of the pylons, because there is a soft seabed. It's very soft. And also, we have a different land motion between Rio and Adirio. Another element at risk is the Dam of Mornos. The Lake of Mornos gives the water for Athens, and we know that it's located in an area where there are a lot of seismic events. So we have to investigate how these different seismic events have affected the dam. The dam is affected by the level of the water. So we see that the red line is the level of the water, and the green line is the deformation. We see that there is a precise pattern of behavior between the level of the water and the deformation over the dam. And this pattern is interrupted by specific seismic events. Not only all the events happen in the area, but from specific events, seismic events. Seems that the dam is affected. And the last period, in collaboration with Technical University of Athens and with Chinese Academy of Sciences, we're working on the Athens Basin area, the broader area, with National Technical University, and with the Chinese Academy of Sciences in the Historical Center of Athens. It's very interesting, the result, because the area is stable. It's stable, the center of Athens, from Kalimarmaro to the Acropolis. The difference in color is the rate of difference, it's 1 millimeter. So it's more or less stable. And now we want to apply TOMOSAR, the new technique of SAR interferometry, in the monuments in the center of Athens. Sorry. We have a great experience also on operational basis. This is very important for the civil protection authorities. This is the case of Santorini, which was made also web story by ESA, and was supported by ESA this. And every month, we make a new map of deformation for Santorini Island during the unrest period. Of course, we apply SAR interferometry in the broader area of Greece, or also in other cases, like in Etna, in Tohoku earthquake, in Sinai, in Alexandria of Egypt, in Amatrice earthquake, in Cairo, and the last one is in New Zealand. This excellent deformation map produced by Penelope, a member of our group. And there is a new one. This for first time, I show you the deformation happened during the 2 weeks before earthquakes in the coast of Asia Minor. And it seems that affect also the northern part. Here is the city of Mythimna, of Mytilene. It seems that it has been affected. These are preliminary results. We want to create another interferogram using another geometry of U in order to be sure for our qualitative results and quantitative results. What we know actually is that there is a different movement between this part, where there were the epicenters of the earthquakes, and the northern part of Mytilene. Sorry, yes. I'm not the Prime Minister. Okay. Okay, thank you for your attention.
Thank you, Professor Parcharidis. Are there any questions for Professor Parcharidis? Okay, I have one. On the slide you showed about Athens, you talked about, I think there is some different change in the color in one of the areas. We can go back maybe. Not so much. Okay, yeah, I think
In this case?
Yes.
But the difference is just 1 millimeter.
Okay. But
It's very few the difference.
Okay, so but it's just different from the other, that's
It's
why.
in the frame of the error, let's say,
Okay.
of the processing.
Okay.
But this area, of course, there are also some other very small spots, red spots, that means that we have a higher rate of subsidence. But we have to investigate carefully these small spots, as this work is in process, and the results will show also the results during the fringe of the fringe meeting of Asia. Because we have a parallel project with the Chinese people, a Chinese city, ancient city in China, and the historical center in Athens.
Thank you very much. Any other questions? No. So I would like to ask Dr. Michas to follow up with his presentation.
Good evening. My name is Georgios Michas, and I'm an AXA Research Fund postdoctoral research fellow at the Technological Educational Institute of Crete. On my behalf, I would also like to salute the initiative of the Greek Supersite and wish best of luck. During the presentation, I will talk about some recent results we had regarding fault growth processes in the Corinth Rift, based on a scaling analysis of the fault populations in various strain regimes. Initially, I will briefly introduce the main seismotectonic features of the area. I will discuss the various strain regimes, and then I will talk about the scaling properties of the fault populations and the implications that arise for fault growth and the fault network evolution. So the Corinth Rift is located in central Greece, and it's a high-strain zone of active extension in the Barkak region of the Eastern Mediterranean subduction zone. The area is known for its high earthquake activity, rapid continental extension rates, and active rifting processes that have resulted in the formation and growth of an impressive normal fault system, making the area an ideal natural laboratory for studying active rifting. In the simplified geologic map here, we see the major faults of the area that have approximately an east to west general direction. The major active faults reach the maximum length of 20 to 25 kilometers, implying that the maximum earthquake magnitude that can be expected in the area is of the order of 6.5 to 7. The next slide shows the recent earthquake activity in the Corinth Rift that counts more than 8,000 earthquakes over a 6-year period. In this map, we can see that the earthquake activity is mainly confined in the offshore zone of the rift. In the western part, that's currently experiencing higher geodetic extension rates, there is a strong spatial clustering of seismicity, while two other special clusters can be recognized in the central offshore part and in the northeastern end of the rift. The earthquake activity has mainly been associated with the active north-dipping faults that bound the south margin of the rift, like the Psathopygon, Aegean, and Eliki faults in the west, the offshore Xylocastro fault in the central part, and the Pischias, Chinos, and Psatha faults in the eastern part of the rift. Some antithetic south-dipping faults are also seismically active, like the onshore Caparelli fault, which along with the Pischias, Chinos faults ruptured at surface during the 1981 earthquake sequence. Sorry about that. So the next slide shows the geodetic extension rates measured by GPS data. Here, the late quaternary uplift rates along the south coast of the Gulf, and the upper crust and whole crust extensions along 3 transects in the Corinth Rift during the quaternary. The geodetic strain rates indicate that active extension is currently focused offshore, with greater rates at the western part that reach approximately 50 millimeters per year, reducing eastwards to less than 5 millimeters per year. An almost similar pattern is shown from the late quaternary uplift rates, where greater rates are found in the central and western parts, reducing to the east to the Perahaura Peninsula and the Megara Basin. In addition, the upper crust and whole crust extension during the last 2 million years have been estimated by Bell et al. By summing the fault heaps of both onshore and offshore faults. Greater extension is found in the central part of the rift, in the area between Akrata and Kiato, reducing to the west. Greater extension in the central part is further supported by the wider extent and larger thickness of the Pliocene quaternary syn rift sediments, and the thickest accumulated sediments within the Gulf of Corinth. So this pattern of long-term extension is in accordance with the late quaternary uplift rates, but in contrast to the geodetic strain rates that are increasing to the west. So this implies that the current extension pattern might be a recent phenomenon. So according to this data, show that the central and western parts of the rift have experienced greater extension than the eastern part during the last 2 million years. Now, in order to study the scaling properties of the fault network, we have constructed a detailed fault trace map for the area. The map here shows only basement displacing faults that have been accurately mapped either in the field or from high-resolution seismic pre-reflection profiles offshore. To achieve high-resolution mapping of the fault traces onshore, we have inserted the existing geologic maps and the fault data that have been obtained in the field into a geographical information system interface. Thereby, using the high spatial resolution 3D topography, the surface geology and cross-sections along its fault, we have precisely defined the fault trace coordinates. In this way, we can directly measure the length the trace length of the fault that is seldom linear, rather than just measuring the linear distance between the tips of the fault. In the following, we will use this fault dataset to study the scaling properties of the fault system. Now, the scaling properties of fault systems are studied in order to gain insights into the physical mechanisms of fault growth and evolution, or to estimate strain in the upper crust. Fault systems are thought to be scale invariant over several orders of magnitude, so that the cumulative distribution of fault trains lengths exhibit power law scaling. This is supported by the similar pattern that the traces of fault populations exhibit across a wide range of scales that may vary from the laboratory scale to plate boundary faults like those that are shown in the image here. In the other image, the cumulative number of 8 fault datasets is shown that cover a wide range of scales, and the corresponding fit according to a power law function that plots as a straight line in double logarithmic axis. However, other natural fault systems exhibit exponential scaling. So in the debate of power law versus exponential scaling in natural fault systems, laboratory experiments and numerical models indicate the transition from the one end member to the other to be a function of increasing strain. This transition is associated with the rates of fault nucleation, growth, and coalescence, which define the main stages of the fault network evolution. These stages are shown in the next couple of slides. According to the numerical model of Spiropoulos et al., at the very early stages of the formation, where few new faults have nucleated, their spatial organization is random, and the size distribution is described by an exponential function. As strain accumulates, more faults are nucleated and grow in size, and starts to coalesce, forming larger faults. At this stage, where growth and coalescence starts to dominate, faults display a power law distribution. At later stages of the formation, strain localizes at few large faults that span the mechanical layer, and the number of active faults decreases. With increasing strain, the fault population reaches saturation, and the size distribution turns back to exponential. A similar pattern is shown in the numerical model of Cowie. This model shows how elastic stress interactions may lead to the localization of strain at few optimally oriented faults. The model formation, strain localizes at few large faults that start to grow by lichens to form larger structures, while other faults may become inactive if they fall into stress drop zones. Now in the Corinth Rift, the fault dataset has 367 faults with trace lengths equal or greater than 1 kilometer. Below this length, the number of faults decreases substantially, in contrast from what we may expect in the field, indicating that the dataset is incomplete in faults below this length. Now, in order to study the scaling properties of the fault system, we use generalized statistical mechanics and the maximum entropy principle. According to this principle, the most probable distribution that describes the behavior of a system is the one that maximizes the entropy, which in our case leads to the Q exponential distribution. The Q exponential distribution exhibits asymptotic power law behavior, and in the limit of Q approaching 1, it recovers the ordinary exponential. So the Q value here indicates how far or close to exponential, thus to random behavior the system is. The inverse of the Q exponential is a Q logarithmic distribution that will plot as a straight line in a semi-Q graph. So this type of analysis shows that the cumulative distribution of fault trace lengths in the Corinth Rift for the complete dataset is described by the Q exponential for the Q value of 1.03. I remind that in the limit of Q approaching 1, the Q exponential reduces to the ordinary exponential. So a Q value close to unity here indicates the almost random organization of the fault network in the rift. In the inset of the graph, the corresponding Q logarithmic distribution is shown that approximates linearity with a high correlation coefficient. In addition, we have discussed previously that the central and western parts of the rift have experienced greater extension in comparison to the eastern part during the last 2 million years. Based on the geologic data, we have divided the rift into 3 strain regimes and estimate the scaling properties of the fault populations. In comparison to the central and western zones, the eastern zone has a greater number of faults, And the cumulative distribution is described by the Q exponential for the Q value of 1.22. In contrast, the central and western zones, the cumulative distribution is described by the exponential function. So this transition here, these results here indicate the transition from asymptotic power law scaling in the lower strain eastern zone to exponential scaling in the higher strain western and central zones. This transition indicates the spatial organization of the fault network in the western and central part of the rift, fracture saturation, and the suppressive of elastic stress interactions in the higher strain zones. Now, a similar pattern is observed if we consider the currently higher strain and lower strain zones of the rift. The current deformation pattern has been established between the late Quaternary and present, and led to the localization of strain in the narrow offshore part of the Gulf and to the Perahora Peninsula and the Alkyonides Gulf to the east. So by performing the analysis, we see that the higher strain zone exhibits, the cumulative distribution exhibits exponential scaling, whereas in the lower strain zone, Q exponential scaling. So the results presented here are summarized in the next figure. The lower strain zones, the number of faults is greater. The average fault length is less, and the cumulative distribution exhibits asymptotic power law scaling. In the higher strain zones, the number of faults is less. The average fault length is greater, and exponential scaling appears in the cumulative distribution. Such results provide evidence for the transition from asymptotic power law to exponential scaling in natural fault systems as a function of increasing strain in the crust, and enhance previous results that indicate a similar transition in laboratory experiments and in numerical models. Concluding, we may say that the results presented here, in analogy with the main stages of the fault population evolution that we saw on previous slides, suggest the mature stage of evolution and fracture saturation in the higher strain zones. In the lower strain eastern zone, the greater number of small-sized faults suggests that nucleation growth may still dominate over coalescence, leading to a scale invariant fault growth and power law scaling. Furthermore, the results suggest that fault growth processes in the upper crust may control the fault network evolution and the localization of strain that are observed in the rift. Once fracture saturation is achieved, faults can no longer grow in length and either increase their displacement rates to accommodate increasing strain, or strain localizes at new faults that start to grow in size. So such a mechanism may account for the slip rate variations and the localization of strain that are observed in the Coin Rift during the last 2 million years. That's all. Thank you.
Thank you, Dr. Michas. Are there any questions for Dr. Michas? Okay. I have one. You think that the approach you present can be used like providing proactively information to the civil protection about the possibility of having an earthquake event?
Actually, yeah, this type of analysis shows where strain is localized and what kind of processes we can expect in these specific areas. So let's say that in the currently active zone of the rift, we expect that more earthquakes, that earthquakes will be nucleated there, and we expect, okay, in the greater future, that more will nucleate and grow in size. So actually, the analysis shows that most of the active faults in the offshore part are yet uncovered and are not included in the analysis. This is the implications, actually.
Okay, thank you very much. Any questions? No. I would like to ask Dr. Sarkas to follow with his presentation.
Good afternoon, Mr. Chairman, dear colleagues. In this talk, we'll try to present briefly the ground deformation studies that were performed in the broader area of Cefalonia-Ithaca Islands over the last 15 years. As everybody knows, the area is very active. A lot of seismic events took place the recent years. In 2014 in Cefalonia Island, and just about a year ago in 2015 in Lefkas Island, showing that the area is very active, and it's very critical to study how the deformation, how the seismicity develops in this area. Just a brief information about the kind of motions that we observed in the area. It is well known that all the southwestern part of Greece is rotating towards the southwest part in a southwest direction, with a constant concerning that the area is stable in Europe. We have velocities up to, we have velocities up to 20 to 25 millimeters per year in the area of Athens, while in the Cefalonia area, these velocities are decreased to about 8 to 10 millimeters per year. For that reason, we established several GPS networks in the broader area since 2000. In 2001, we established the network in Cefalonia. Earlier, we had established in 94 the network. In 94, the network in Patras Gulf, and in Zakynthos in 2005. And also, there are several continuous GPS stations that are operating in the area over the last 10 years, especially after 2013. Many stations belonging either to National Observatory of Athens or a Metrica company are activated in the area and give us quite a lot of information about the ground deformation that taking place in this broader part. Just a brief presentation of the work that has been done to Patras Gulf. As I mentioned before, we established the network over there in 94. In 2013, we start processing data from continuous stations in the broader area, and there is a quite good match between ground deformation observed by our local GPS network and the network, the continuous GPS network that is working in the broader area. Similarly, we have done quite a lot of work in Zakynthos Island, GPS measurements, interferometric results, and of course, seismic study. Let's go on now to Cefalonia. The network was established in 2001. We have measured many points, many times all these years, focusing mainly to study the ground deformation along the major tectonic features in the area, thrusting zones, and also we divide the area to main tectonic blocks, and we establish stations along the tectonic blocks to study the motion of the broader area, as well as local tectonic features and local tectonic zones. The network in Ithaca was established just in 2004, but was not measured very often. We focused to the Ithaca area mainly after the 2014 earthquake sequence in the western part of Cefalonia. For the first period of measurements, 2001 to 2010, the main seismic events that occurred in the area was the 2003 Lefkas earthquake with a magnitude of 6.3, and the seismic sequence in the southern part of Zakynthos during the 2006. As you can notice from the seismic sequence that took place in Lefkas, the post-seismic activity has moved southwards towards the northern part of Cefalonia. The differential measurements of the GPS network during that period showed, with respect, a stable point in the center of Enos mountain, just 0.06, so a kind of rotation of Cefalonia around this pole, with intense uplift occurring in the area of Paliki Peninsula, and differential motion between northern and southern part of Ithaca. For the same period, we have, via a project that was established by ESA and the Terra Firma project, we have done PS interferometry, TRE actually from Italy, Milan, Italy, has done PSI interferometric processing in the area using ERS data covering the time period from 92 to 2000 and NDSAT data from 2003 2008. As you can see, the two images for the two distinctive periods are quite different. In the first period that covers the period 92 to 2000, we can see a stability, very small velocity values, while in the next period we see more stronger motion with a higher magnitude of velocity values. For each data point, we have the time series, we can have the acceleration and the velocity of each data point. Acceleration is a very important parameter because we can see the kind of the rate of the motion, if it is accelerating or decelerating. And the highest values of acceleration were observed in the northern part of Cephalonia, in Paliki, northern peninsula of Cephalonia, and in the southwestern part of Cephalonia. These are the values, the areas where the higher amplitude rate we have was observed. In 2014, we had the two strong events in Paliki Peninsula that caused significant damages to the island. Ground deformation monitoring was not feasible at that time because we have stopped our measuring quite a long time ago in 2010. We revisited the area in 2014. Based on the velocity values that we had calculated for the previous time, we were able somehow to evaluate what was the coseismic deformation during the event of 2014. And you can see that actually the stronger deformation occurred in the area of Paliki Peninsula with differential motion between the eastern and western part in both horizontal and in vertical direction. To model the data, we use two faults coinciding. Actually, we use two faults that combine with the GPS measurements, and we try to establish if we have a single fault or two different faults. In the end, we concluded that we have to deal with two different faults that actually belong to the same faulting system. The first event was associated with the southern fault that has. Oh, sorry, what have I done? Okay, yeah, we have two main faults in the area. So we associate the first event with the southern fault, the second event with the northern fault. The two faults have similar parameters, as you can see, azimuth, depth, dimensions, and deep and the slip. And we concluded that actually it is two different faults, but they belong to the same faulting system. From 2014 to 2015, we remeasured the network in 2015 again. In this time period in this period of time, we haven't seen any strong deformation. We've seen actually that the island exposed a similar kind of ground deformation as was observed before the event of 2014. And then in 2015, we had the strong event in Lefkas Island, with magnitude up to 6.2 and a post-seismic sequence that also moved towards. Sorry, I'm doing something wrong over here. Yeah, maybe if I keep it a bit longer.
You need this one?
Yeah, it's okay. Yeah, it is. Yeah, this slide. As you can see, actually, we have observed type of motion that is the anticipated type of motion for the broader area, with differential motion between the northern part of Cephalonia and Ithaca, as well as in between the northern and southern part of Ithaca. We had the strong event in Lefkas. We've seen the, sorry. The seismic sequence that moved towards south, and the strongest deformation observed in the two GPS stations that are located in the Lefkas Island. The pond station that is located to the south had exposed the highest deformation that was about 20 centimeters. But this earthquake caused quite a lot of motion, even to stations that are located away from the epicentral area. In Cephalonia, we have noticed deformation that occurred also in VLSM station, the central part of island, or even in Scala area, in the southern part of island. But also we have noticed deformation in Zakynthos Island, as you can see over here, in stations that located in Agrinio area, in Etolokarnania, in KTCH station. KTCH station is located close to Mesolongi area in Etolokarnania, but we have not noticed any ground deformation in Peloponnese, in Patra station, or in RLSO station that's located to the western part of Peloponnese. This is actually the arrows, the vectors that you can see the horizontal motion during the earthquake of Lefkas in 2015. The scale is different. Over here, the black arrows is 10 centimeters the scale, and over here it is 1 centimeter. But you can see that the effect of something. I will stop using it. You can use the mouse. Yeah, I can use the mouse. You can. You can see the strong deformation in that observed also that this the earthquake affect also the broader area and not only Lefkas. As it was expected, the strong emotion that was observed also in Cephalonia. These are the results from March 2015 to February of 2016, just 1 month after the 2 months after the earthquake occurred in Lefkas. The strongest motion was observed in the northern part of Cephalonia as well as in Ithaca, but also other places exposed, other stations exposed quite strong and quite significant ground deformation. Just to summarize our key points from the study, how the island behaved during these two events, I mean the event of 2014 in Cephalonia and the 2015 in Lefkas, we can say that the 2014 earthquake, it was a more local earthquake affecting mainly the island of Cephalonia, while the 2015 earthquake was a major earthquake in the broader area located, as was published this year, along the Cephalonia Transform Fault. The 2014 earthquake was modeled using two different faults, but they belong to the same faulting system. We have a kinematic boundary in between Paliki and the main island of Cephalonia, as well as in between the northern part and the northern peninsula of Cephalonia and the main part of Cephalonia. And also we have seen and we have identified differential motions along some main thrusting zones in Cephalonia, as well as differential motions between Cephalonia and Ithaca. Generally speaking, studying the strain rate field of the area during the period 2014 to 2016, we can say that there is differential motion between Cephalonia and Ithaca, and we have compressional forces in between these two islands during interseismic periods and extensional forces when during coseismic periods. So during interseismic periods, we have approached somehow. We are approaching the two islands, approaching each other, while in during a major event, we have expansion of the area in between them, so the two islands move away. Quite a lot of results. We can have quite a lot of results, and we can conclude many conclusions if we study the time series from the continuous GPS stations that are available now in the area. Generally speaking, we can say that the stations that are located over here, I'm showing you the time series from Span and Pond station, the two stations in Lefkas, as well as in Valsamata area. The Span Pond show a long-term periodicity of about 200 days, while in VLSM station that is farther away from Cephalonia Transform Fault, this time expands to 1200 days. Also, if we notice the VLSM station time series, you can see that there is a type of change of the velocity field, of the velocity of the northern component during the period before the earthquake in 2014 and after this event, while the east component, up component are not showing any significant changes. Another quite interesting feature is that the baseline, I mean the distance between the stations in the Lefkada Islands, Pand and Pond, showing a continuous decrease during the years before the earthquake occurred. After the earthquake occurred in 2015, we've seen that you can see that the velocity now it is increasing with up to 2 millimeters per year, while in a similar period before the earthquake, the distance was decreasing with a higher value of up to 4.5 millimeters per year. The distance also between the Valsamata and Pond station, I mean the Cephalonia and Southern Lefkas, was increasing before the earthquake of 2014, and even higher with a higher rate after the earthquake of 2014. And now we see that in between the period from after the earthquake, there was a relaxation, post-relaxation period. The baseline was decreased, but now it's stable, the whole area. And if we compare the time series, the baseline, the length of the distance between Zakynthos and Valsamata and Kefalonia, we see that the area shown shortening, and this is supported also by the strain field that shows that compressional forces appears that are accumulating in the southern part of Cephalonia, in between Cephalonia and Ithaca. Just to conclude, I would just want to point out some remarks. Although this is a quite old image, this is the PS image that was produced based on Envisat data. We've seen that the early 2014 seismic event that occurred in Cephalonia is coincide with the area that shows the highest velocity and acceleration value. Also, the Lefkas earthquake in 2015 seems that is in accordance with the observed high velocity values that were observed in the northern part of Cephalonia. And maybe we can say that increased velocity values in Ithaca can be associated with the Lefkas event. And I think that we have to point our interest, and we have to focus in the southern part of Cephalonia, where also high increased velocity values were observed. It is a thrust zone. It is well known that thrust zones are giving quite big events, and maybe this image, when we combine it with the lack of any significant seismic activity in the southern part of Cephalonia, may indicate that we may have a strong event in the future. However, this is an old image. We have to use new data and study the whole area. And I have the feeling that in the framework of Enceladus Supersite, we have to focus in the broader area of Cephalonia because it's going to be very active in the future. Thank you very much.
Thank you, Dr. Sagas. Are any questions? Okay. Thank you, Vasilis. So I would like to ask Dr. Nikolakopoulos to follow up.
Good afternoon, ladies and gentlemen. Except of the earthquakes, as you all know, landslides also provokes casualties and damages. So I will speak about active landslides in the frame of the Greek supersite. The outlines of the presentation. First of all, a few words about the Laboratory of Engineering Geology. Then some words about our activity, research activity, some case studies, and the summary. The NGO Lab was founded in 1988 by Professor George Koukis. Right now, head of the laboratory is Professor Nikolaos Sabatakakis, and the laboratory staff is consist of 2 PhD postdoc researchers and 7 PhD students. And also my team, the remote sensing research team, collaborates with the NGO Lab. The research activity of the NGO Lab, how the geotectonic, the geological condition influence the technical works, the constructions, and the impact of all of that on the geo-environment. Also, we study the landslide hazards, and we try to monitor landslides using both in situ measurements and remote sensing data. The laboratory has participated in many national and European programs. You can see some of them in this slide, in collaboration also with the National Observatory of Athens and other organizations in Greece. The Laboratory of Engineering Geology holds a very large inventory of regional landslides. We have a long-term monitoring data. We have a big experience in remedial measures, design, and also in engineering, geology, and geotechnical works. Some case studies. First of all, you are all familiar with the Panagopoula landslide. It's on the national road from Athens to Patras. Also, another one, big landslide, Karia landslide. Analypsi landslide, Platanos, Platanitis, and the newest in Myra, a village outside of Patras. A few words about the Panagopoula landslide, maybe the most famous landslide in Greece. The first event was on 1971, and 1 year later, a sudden mass movement occurred, and the national road was blocked. We have inclinometer measurements for many years, 3 main series of measurements from 1995 to 1997, from 1998 to 2009, and more recent from 2013 up to date. We have 22 inclinometer boreholes in the area. Some air photos showing the Panagopoula landslide event, the earth photo from 1945, and the next one from 1972. And you can see here the area of the landslide. As I told you, we have continuous measurements. So we can say that right now we have a landslide extremely slow. The velocity of the landslide, it is active, but the velocity is extremely slow, about 0.02 millimeters per day, or in a total 8 millimeters during the last 2 years, from 2015 to 2016. The Karia landslide, another one, big landslide. The first failure was recorded in 1962, the second one in 1999, and 2 years later, in 2001, again, the landslide was reactivated. We have also here many inclinometer measurements, 2 series of measurements. You can see here the dates, and also some photos and earth photos showing the area that was affected by the landslide. We have measurements about the velocity of the landslide. And the last case that I will show you is the Analepsy landslide. The first event was in 2014. A year later, on February and March 2015, the landslide was reactivated. It has totally destroyed the main road and 2 houses, and there were a lot of cracks inside the village. Here are some photos from the landslides. It's me in one of the gaps, the main road of the village, one of the destroyed houses, a second destroyed house, and some gaps out in the fields. And in Analepsy, for the first time, we have performed a complete monitoring project. That means that we have a topographic survey, GPS campaign, inclinometer and piezometric boreholes, high-resolution satellite data, UAV data and photogrammetry, and finally, we try to monitor the landslide with interferometry. A few slides. First of all, the topographic survey just after the event. We have put a lot of targets in the buildings all around the village in order to measure them every 3 months. A sketch, a topographic sketch. Also, GPS campaign, extended measurements. We have thousands of measurements inside and outside of the village. And also we have created a map showing the depletion and the accumulation zones. For example, an area where the accumulation is observed. We have also 2 inclinometers boreholes and 1 piezometric boreholes. The first one is outside of the main scarp, and the other is inside the landslide. And our team is measuring the boreholes every month. Some figures, the location of the 2 boreholes, and the diagram showing the movements. We have also used high-resolution satellite data, Gold U2. Just a week after the event, we took an image, a satellite image, and we have mapped the damages. The background image is orthophoto from the Greek cadastre. And also UAVs. We use UAVs to make photogrammetric flights every 3 months over the area. We create orthophotos and we measure the movements on the buildings. As you can see here, the overlap of the several orthophotos. And finally, we start to put some persistent scatterers in different parts of the village, inside the village and inside the landslide, in order to start monitoring the landslide also with interferometry. Summary, the NGO lab has a very well-documented sites of interest along the Greek supersites. We have a long time series of measurements, and we try to monitor the landslides using different methods like optical and radar and UAV data, and also in situ measurements, inclinometers, GNSS measurements, etc. Thank you very much.
Thank you, Dr. Nikolakopoulos. Any questions for Konstantinos? No. It seems that you have a good data set, especially in analysis. What is the plan? What is the plan for data fusion on these data? And you are going to try to see with the continuous GPS measurements and the interferometry, they will comply one to the other. You expect they comply?
The basic is that we have at the same time measurements and the bedrock, the depth of the movement. So we try to fuse those measurements with the remote sensing measurements in the surface and find how the main core of the landslide will move in the future.
Do you have an end use?
The local authorities, the prefecture of Western Greece.
Do you get any funding from the prefecture of Western Greece?
No.
Okay, I hope you soon have. Thank you very much. So we will have a small break now for half an hour. We will come back at a little bit after 5:10. We will have we'll connect with the GEO in Geneva. So the GEO Secretariat, Mrs. Barbara Ryan, will have a welcoming address for the meeting. And we have a small change for the afternoon session. Dr. Sakellariou, unfortunately, he's on a field trip in the Aegean, so it wouldn't be possible to have his presentation today. Thank you very much until now. I'll see you in half an hour. Can you hear us? Up. I can speak. Okay.
Hello?
Is it better? Okay, it's better.
Oh, but it's by Skype. So is it fine for you?
Yeah, it's fine.
Okay, let's just keep it like that. So we will disconnect from the other.
Wait a minute. Can you move close? Okay. Okay. Wait a minute.
I was saving some room so you could see Vanessa too, but we can do this and then I can show the camera to her.
Okay, it should be okay. Can you see? I have to just.
Okay. And then you just, when you want us to start, Alexandros. Oh, good. Yeah, can see the crowd. Oh, that's much better. Oh, that's great. Okay, very good. Let's see, shall we go ahead and get started?
Yeah, is everybody inside? Yeah. Just give us a minute.
All right. You tell us when. Thanks, Rick. Yeah, we can hear you perfectly. How about the audio on your side? Can you hear us? Okay. Okay, great. Well, listen, thank you. First of all, thanks for the invitation. For those of you who don't know me, my name is Barbara Ryan, and I'm director of the Group on Earth Observations, the Secretariat here in Geneva. And I'm joined by Vanessa Allen, who is on secondment to the Geosecretariat from Switzerland. And while she was seconded to do water primarily, our former disaster coordinator had left, and so she's covering both disasters and cold regions for us. So thank you, Vanessa, for that. But first of all, thanks for fitting us in, because as I'm looking out over the audience, it's nice seeing some familiar faces. So Maria, who used to do an internship for us, and of course Betty and Harris. So thanks you guys for all of that work. I know this is the kickoff meeting for the Greek Supersite, and it's going to be quite important, not only for what's happening in Greece, but I would argue for the entire Balkan area, and then how it fills and feeds into our geohazard supersites and natural laboratories, so the whole GSNL effort. What I wanted to do, though, is set a little context for the importance of the work, because you know that our primary objective is to just make sure that decisions are informed by coordinated, comprehensive, and sustained Earth observations. And at the end of the day, it's largely national governments that are making those observations. And so the work that's going on in Greece, whether it's in the universities or at the federal government level, is largely funded, or in the private sector, a lot of times is funded by national investments. And so at the GEO 13 plenary in St. Petersburg, and some of you were there, the plenary adopted 3 engagement priorities across the entire GEO work program. The first one was the Global 2030 Agenda, or the Sustainable Development Goals, and those 17 goals. The next one was the Paris Agreement and climate, so with UNFCCC largely as the policy mandate. And the third really important one was following up the Sendai framework and disaster risk reduction. And so while you might argue that what you're doing right now with the Supersite feeds each one of those, particularly for the Sustainable Development Goals, we've likely in GEO categorized your work under the third engagement strategy, which is the Sendai framework and our DRR work. So absolutely what you're talking about today, tomorrow, will in fact feed into our engagement priorities with the global GEO effort. I think maybe, well, a couple things. Certainly there's going to be data that you're generating. It's not just space-based data, but it'll be a lot of in-situ data. And you know, this is the challenge that we've had in GEO. The sheer volume of space data in GEO, in our GEOS common infrastructure, leads people to believe that we are only interested in space-based data. And so another thing that both the Mexico City plenary and the Russian Federation plenary did, say more coordination on in-situ observations needs to occur. And so again, what I would just ask is that for any data that's being collected from the super sites, first of all, advocate that it be broadly and openly available, and then also that it feed into more of the in-situ coordination that needs to take place globally. So there's a lot of data, and that's a really important part of what needs to go on. And then I guess maybe just in closing, you know, we do have, again, following the Sendai conference, we do have an initiative called GeoDharma, and there are some key member governments. We hope you join that. There are some key international partners, UN, ISDR, the International Strategy for Disaster Reduction, UNISAT, UNITAR, and UN-USA. So member countries, participating organizations coming together in that global initiative known as GeoDharma, and we sure would want to make sure that your efforts are ultimately serving several purposes. So I think, I know it's late in the day for you there. I think what we thought maybe we would do is just stop, and then Alexandros, thank you, but if there are any specific questions from the audience, then we've got a little time on this end, and we'd be happy to answer any to the best of our ability. So I'll stop there. Thanks. Oh, shy. Everybody's shy. All right. Well, Vanessa, do you want to say anything so at least they'll hear a voice and be able to put a face with that voice?
Then they can hear my voice. Hello, everyone. So I'm the, as she said, I'm the seconded by Switzerland. I'm the water expert initially, but I also take care of the disaster activity. So if you have any requests from the Geosecretariat, it pass by me, actually. And I will attend in March the CEO's working group on disaster. And I think some of you will also attend this meeting, so I'm looking forward to meet you for real. And if you have any question before this meeting, please don't hesitate to send me an email that you can find on the website of earthobservation.org.
You can follow the link I have provided so that you can follow our presentation if you like.
Yep. Thank you very much for that. And I think you probably have called in some of the time this afternoon. Or
Yeah, and I will continue to follow the meeting until it's finished. So I'll be there.
All right. Thank you, everyone. Good luck, and really, just drop an email if there's anything we can do on our end. Appreciate it very much.
Thank you.
Bye. Thank you.
Hello from me. The objective of the present talk is about to give a short description of issues discussed in supranational ground motion service, a workshop that took place during November in Begiar, Germany. A critical mass of INSAR community has developed in European research institutes, academic institutions, and private sector. National activities have been established, as it is shown in the following presentations that took place during this workshop. We start from Germany. The activities that are accomplished or planned refer to establish a nationwide surface motion data set based on all available Sentinel-1 imagery. Integrate with other measurements, mainly GNSS, geoscientific validation is quite important, and also update the data set with application services. The status on the ground motion service in Germany refers to collaboration with geodetic services of GNSS calibration, collaboration with responsible authorities for definition of application-specific products, and a first Sentinel PSI map of Germany is going to be accomplished within 2017. Another application is from the Norwegian colleagues. A project has been established with financing from the Norwegian Space Center in order to develop a dynamically updated nationwide deformation map. The information will be available to all via easily accessible web maps and tools. During 2009, anyway, it's moving. During 2009 to 2016, an operational regional service has been set up. Today, activities include scaling up the Sentinel-1 data, radar SAT-2 data, and the first national-wide Sentinel product is going to be ready soon. Of course, future activities are to have an operational service with Sentinel-1 data, include semi-automatic processing and dynamic updates of this data set. They are willing to share experience in building the nationwide service. Of course, the mission is not yet accomplished. Sentinel-1 data are quite new, but they're open to any collaboration with so as to develop different products on different levels and capacities. Another example is coming from the Netherlands. They have accomplished an integrated model has been established so as to monitor the whole of Holland with accurate measurements because they have quite a lot of problems with the coastline. So they have developed all this integrated model, and they include the Sentinel data in order to get more information and up-to-date data sets. Italy. According to Italian colleagues, the technology is ready for large-scale SAR data processing in order to provide monitoring services at national European level. Sentinel-1 data is the best candidate to those possible services. IREA CNR is involved in the generation of displacement maps and time series with Sentinel-1 data at the scale of the Italian territory. And quite a lot of ministries are involved in order to accomplish these maps for the whole of the territory. Some support that we get from the Italians is do not forget to use historical missions. They are quite important. EPOS for data and product integration model is quite useful. ZEP for the platform architecture is free and can be used by all. A supranational motion service is potentially of strategic interest for Europe. For Europe, and member states focus on the creation of a sustainable infrastructure and not only on provisioning final products. Ground movements in Belgium is also quite important to monitor. Sentinel-1 data are to be processed in order to get up with up-to-date info. INSAR in Poland, the Polish Geological Institute has a strategic investment in INSAR technique. State-of-the-art time series INSAR have developed, and 3 generations of time series algorithms have been implemented. First, distributed scattered INSAR, second, persistent scattered interferometry, and homogeneous distributed scatterers are to be developed in the near future. Of course, it's quite important to have continuous focus and priority on INSAR quality control. Corner reflector sites for validation and integration activities are quite important. PGI INSAR TBX is quite important for strategic investment in software and algorithms. The other example comes from Denmark. This is a low-lying country. Collaboration with end users to tailor product-specific needs developed in the country. A great effort has put into create awareness of data, ensure understanding of measured signals, ensure use of data. In Spain, the safety project has developed in order to provide to the civil protection authorities the capability of periodically monitor and assess the impact of geohazards. And they have a lot of experience on applying INSAR processing. CNES is well aware of the potential of the INSAR technology and the Copernicus program, and has already planned a set of activities aiming at a national service based on Sentinel-1 data. An area of about 2,000 square kilometers has been selected. On this area, all products, deliverables foreseen for the national service will be generated and evaluated with sorry. This one. Go back.
It's fine.
No, it was this. Oh, yes.
But don't use the mouse. Please use the.
I use this. It's a key features for national service for France are data usability, reliability, regular update, as well as the training program for all potential users. The planned service is viewed as a brick for building a supranational European service in the Copernicus framework. IGME is the National Institute in Greece, has been applying INSAR in interferometry within cooperative projects like Terra Firma, Panzeo, and also the most recent projects of Memphis and GeoGrandly. Memphis is a current project that proposes a set of Earth observation data processing methods and ITT solutions to produce landslides and seismic hazard maps. 2 areas within the area of interest identified in the Greek Supersite initiative have been selected as pilot project areas of the Memphis project by the IGME Engineering Geology Department. Also, some collaborative work has taken place in working within the Memorandum of Understanding with the Beyond project. And we have interpreted 2 cities, one Volos and the Igoumenitsa city. Mean temporal velocities from descending track 93 covering the periods 203 to 10 have been interpreted. We have seen velocities in the harbor minus 4, minus 9 millimeters per year. That's a subsidence in the harbor area. Landslides, there are active landslides near the area, and they have well related with subsidence. Also in Volo cities, we have subsidence in the harbor area again, and in the slopes around the Volo cities, where again we have a subsidence of -5, -9 millimeters. Now, the IGME perspective is for the exploitation of multitemporal interferometry velocities in terms of coupling MTI results with field investigation, new landslide detections, new subsidence uplift detections, give solution to geotechnical problems of the area. Secure Earth observation data legacy of previous projects, provide Earth observation, and improve monitoring techniques for supporting and developing aspects of the society. In Greece, there is a lot of expertise in using INSAR, but we have to develop a national policy more coherent as the other countries did, the other European countries did. Now, why a European initiative? BGR and colleagues from European partner countries have started or are planning to establish nationwide Copernicus Sentinel-1 based ground motion services. They are based on both research centers, institutions, and they are linked to universities and the industry. The idea of a supranational ground motion service has been discussed on different platforms, recently EU Commission level, the EU Copernicus User Forum, at German National and European Geological Surveys. This is a European initiative that might be able to support the GSNL planned activities in the future. The discussion is still open, and you can contact our colleagues in BGR or the Earth Observation Group of the Eurogeo surveys. I have a short announcement now to make. The Geological Society of Greece has established a new thematic committee in 2016. The new GSS member is the Remote Sensing and Space Application Committee, and all interested parties that are working on this research field can join this group. I think the most is dissemination and cooperation are the most important tools in forming a national policy in Greece and to cooperate between each other. Thank you.
Thank you very much. Are there any questions for Mrs. Stefouli? Yes, Stefano.
Services for providing this kind of information. Is this integrated in EPOS or is this?
There is a suggestions from the Italian partners that EPOS is going we have to be based on EPOS and also to use JEP as a platform for processing INSAR data. But there is still an open discussion because, as you see, the Norwegian people work with their own algorithms. The Polish people are working with their own, and so there must be more coordination between each other in order to achieve something better than what they already have.
Okay, thank you very much. We move on with the presentation of Mr. Maltezos.
Good afternoon. My name is Evangelos Maltesos, and I will present our work with Mr. Briziotis, Haralabos Manis, Beti Haralabopoulou, Manuel Drovithis, Manuel Kirtas, Konstantia Makra, and Alexandros Savaidis, which is about LiDAR, airborne, and satellite processes for change detection in urban environments prone to geohazards. And as test site was the Kalahari area at Delta Municipality. First of all, I want to mention that this study aims to implement automatic change detection processes to complex urban areas via computer vision algorithms by exploiting time series data such optical data, such aerial or satellite imagery, and point clouds either derived from LiDAR laser scanning systems or by dense image matching techniques. Secondly, we introduce an effective and sophisticated built-in change detection frameworks from LiDAR or dim point clouds. The outline of the presentation are some slides about some introduction information. Then we will talk about the use data, then for the change detection techniques, then for the built-in detection from the point clouds, and finally the conclusions and the outlook. The change detection is a research field for more than 2 decades. There are several techniques. First of all, the first technique is by using only images. The second is by only point clouds, derived from LiDAR or dense image matching, and a combination of the two. The change detection techniques in the literature are 2. The first is the change enhancement, which is a detection of the location and the size of the changes. And the second is from 2 approach. When we can detect the location, the size, and the nature of the changes. At this study, we implemented the first approach. So about concerning the data time series, we had for 3 periods, this, and this. For each period, we had several data. For the first period, we had aerial images and orthomosaics with a ground sample distance about 20 centimeters, and the corresponding point cloud derived from dense image matching. In the second period, we had aerial imageries and the corresponding orthomosaic with a GSD about 10 centimeters, and a point cloud derived from laser scanning, aerial laser scanning system. And the third period, we had 3 types of data: the satellite imagery from Worldview 2, and aerial images, and the point cloud derived from dense image matching. So we can see the region of Kalahari and the associated data. This is the colored 3D point cloud for a sub-region. And this is the point cloud, the color infrared point cloud, where with red points are the vegetation points. This is the second period, data period, second period, aerial imagery and orthophoto. The LiDAR point cloud colored by the intensity values. The satellite imagery of Worldview 2, and aerial imagery, and the corresponding dense image matching point cloud. About the change detection, we implemented for the first and the third period by using only image information. For the first was about aerial images, and the second from the ortho image derived from the Worldview 2. And this is the result. By implementing this algorithm, this result was extracted in the ERDAS imaging software by using the sophisticated Delta Q tool, where with red pixel values are the changes at the new period. And this is a zoom in at here. Here we can see a building that does not exist at the first period, and the new, and this is the changes. Then we implemented the corresponding change detection only by using 3D point cloud. So we had, for the first period, the 3D point cloud from dense image patching, and the second from the LiDAR. And then we calculated the distance between the 2 point clouds, applying a cloud-to-cloud point cloud approach via a closest approach technique. And these are the results. With blue values are changes, with very small changes, and with green values are the changes. This is an effective approach since, as we can see here, by implementing just a change detection technique only by ortho images, we can see some changes, but here there are no changes, since we implemented just a height difference. This is a zoom in. Of course, we can implement a thresholding process to filter insignificant changes, and to implement some thresholds associated with typical building floor, about 3 meters or something else, whatever we want. And this is a change detection from the second and the third period. We implement again a change detection between the aerial image and the satellite imagery. And these are the results. Again, as we can see here, there are no differences. And by using only aerial images, this is an example with a building change detection and a vegetation change detection. And again, by implementing change detection between the point cloud with LiDAR and dense image matching. These are the results. So this is the second part of this presentation, which is about the building detection from LiDAR or dim point clouds. In the literature, there are 3 approaches. The first is via a normalized digital surface model from LiDAR data, and if we want to implement an edge map. The second approach is via filtering techniques and edges directly at the LiDAR data. And the third is from colored infrared dense image matching point clouds. So about the first, these are some results that we extracted. These are the building polygons that they had some attribute values corresponding with their height or their area or some other geometric characteristics. This is the second technique. This is the main framework. We have a LiDAR point cloud. We can compute the normals for each point, and then we can remove the vegetation via filtering process by using the normal distribution. And then we can extract the vegetation and to remove the terrain, the bare earth, and then the remaining points are the buildings. These are some results. With blue points are the building points. Of course, we have some false positives values associated with some detected vegetation as buildings values. This is the second proposed scan line smooth filtering technique. This is a framework that we did in order to extract the 3D building models in level of detail 1. These are the building points studied by the filtering approach. This is the DSM, the digital surface model, and this is the edge map. And finally, we can extract, if we combine these projects, we can combine the final 3D models of some region. And the third approach is by using only images and especially a density match matching point cloud. Again, we can implement the same framework by removing the vegetation, by calculating a vegetation index, and finally, we can extract the final point cloud of buildings. This is an example here. We can remove the vegetation, then we can remove the terrain, and the remaining points are the buildings. And these are some results. Of course, here again, we have some missing parts of buildings associated with mismatches at the stereo processing procedure. And finally, in conclusions, the constant technological evolution in computer vision enables the development of automatic and efficient change detection techniques that can be used in urban environments prone to geohazards. And thus, by using automation, we have rapidity, accuracy, and economy. The proposed change detection approaches exploit multimodal data. We used satellite images, aerial images, point clouds derived from LiDAR, point clouds derived from aerial images. So all these the mentioned frameworks are flexible in cases that only one type or lack of various data exists. The extracted building detection results by the proposing building detection frameworks can be used for several applications, such as cadastral, urban and rural planning, etc. And of course, to critical infrastructure monitoring, spatial analysis, and from two, as I said at the beginning of my slides, change detection applications. And finally, the future world will focus on improvement of the building detection results, as well as to the use of further data, such UAV imagery or some images or other additional information. Thank you for your attention.
Thank you, Mr. Maltesos. Any questions? No questions. Okay. You think all this workflow you have developed and you follow up, it's a procedure that is easy for someone to follow in the future for other areas, given the fact that you have the appropriate data? I mean, LiDAR, satellite imagery, or UAV data?
Yes, that was the main scope of our work, to implement several workflows and frameworks, and to use several types of data in order to make a global framework. So, of course, we can implement such frameworks at other at other urban environments with other building structures. Of course, at the learning data are different, or buildings have different building structure from others like Germany or some others. But we think that it's a global technique because we don't use many parameters, but thresholds by using some indices.
Okay, thank you very much. So we move on with the next talk is Dr. Chrysoulakis.
Okay, good afternoon. I'm Nektarios Chrysoulakis. I'm Director for Research at FORTH, the Foundation for Research and Technology Hellas, and Head of the Remote Sensing Lab there. This presentation does not belong in the core activity of the Greek Supersite, because it's related rather to monitoring the sensitivity, the heat fluxes in urban areas. But I would like to explain how we can develop synergies with the work that is done in this Supersite and the data which are produced for other activities. Of course, I come from FORTH. And besides my lab, there are two other labs that are involved. The group of Professor Makridakis and Professor Skatsoulis, which are involved in wave propagation, and they're very much interested in collaborating with the seismologic community. And Professor Apostolos Aris from Institute of Mediterranean Studies, which is involved in geohazards monitoring, especially in archaeological sites. So we're not working in geohazards, but we are we're a small group, but very active. We have 4 Horizon 2020 projects running simultaneously this period, and we have very actively involved in FP6 and FP7 research. And we'll focus mainly on fires and floods, but mainly on urban climate and urban heat fluxes, urban planning, and heat waves. So I'll give some examples that how can develop these synergies, as I said before, especially for urban planning. And this is an example that's an article that was published in Nature last year. And there are several interviews with several famous scientists in the US, calling from large-scale implementation of mitigation technologies in cities. And you can read the main message here from Brian Stone Jr. that says that if you're just putting green roofs at City Hall and schools, it's not going to move the needle. That needs we need large-scale implementation of this type of technologies. And since there are large-scale implementation, the potential of Earth observation is much higher. In Europe, there is an initiative of nature-based solutions from DG Research. They have funding several projects. They have given more than 100 million euros funding these projects over here. You can see these projects have just started. Very large demonstration projects for related to the implementation of nature-based solutions. And this one, Think Nature is the umbrella. Participating in this follows the work that is done in all other projects. And we've tried to involve Earth observation in monitoring and evaluating the implementation of nature-based solutions in cities. And by monitoring, I mean not only the classic change detection activities, but also try to see how the heat fluxes will be changed after the urban intervention by urban planners in cities. So I will not go in deep with this energy budget that we work in urban fluxes project, but I will focus rather on turbulent heat fluxes, which is okay. Here we can see the urban energy budget inputs and the incoming energy that a part of it is stored in buildings, the urban volume, and then transporting turbulent wave the atmosphere as sensible heat flux. This flux or a part of this energy is used to evaporate water. That means latent heat flux or evapotranspiration. And we have several case studies. One of these is Iraklio, our cities who have developed in situ networks of meteorological stations, very dense networks, measuring the surface temperature and the air temperature. You can see the gradient here. And since we have a gradient, you have flux from heat from the surface, the atmosphere. And we have also installed very specific installations with eco-variance towers. This is an example of the Tower of Heraklion, which is here in downtown. This is the 3 months footprint that was installed 4 months ago. And we measure directly the fluxes, the sensible heat flux, the latent heat flux, and the CO2 flux in the city of Heraklion. And we have developed also algorithms to downscale temperature, thermal infrared information, capable of deriving temperature information from combining Sentinel-2 and Sentinel-2 images, because our output scale is the more relevant for urban planning scale, which is 100 by 100 meters. But we start from disaggregated data, very high resolution data, but the fluxes are calculated in a grid 100 by 100 meters. And I've developed algorithms just to be able to compare and validate the temperature that is downscaled from thermal infrared radiation, taking into account the different field of view which the radiometers on our towers can observe the cities, because it is completely different from the nadir view of the satellites, because the radiometer can see also, you can see this fisheye view here that can also see the walls of the buildings. And we compare and validate the temperature, and we can able to calculate the thermal heat fluxes, and I will focus on sunset heat flux. So we have surface temperature measured by satellites, air temperature measured by our sensors, and we have developed algorithms just to overcome the change of support problem from PI measurements to transport these measurements in grid. And of course, what is related to this work in the site is this parameter, which is the aerodynamic resistance, and can be extracted from morphometric analysis. So we have satellites here, which is surface temperature, air temperature from in situ measurements, and aerodynamic resistance from 3D city models we developed from satellites. And this is an example for Heraklion. We've developed very detailed 3D model, not only the buildings, but the trees also. We know what exactly each specific tree is in Heraklion, and if it is evergreen or broadleaf tree. And we need to calculate, to have estimation how compact is the city, because it is related to the fluxes and the flow of wind and all these turbulent fluxes. And we need to know indicators like this one, which is the plan area index, the frontal area index, or the canyon aspect ratio. And from these parameters, we can calculate Z0 and ZD, which is morphometric parameters related to the roughness of the surface. So from mean building sky and tree sky, calculate LP and LF, which is plan area index and frontal area index. And from this, we can calculate resistance, the aerodynamic resistance. And since we have the eddy covariance tires, we can validate all these measurements from morphometric analysis from wind profiles we measure in the towers. This is an example also from latent heat flux and sensitive heat flux. This is an example of the city of Basel, which is also in a case study. I said again that the output range is 100 by 100 meters, but we're starting from disaggregated data. Concerning the heat storage, we have the element surface temperature analysis method, and we need to calculate the fractions, the fraction of walls, the fraction of roofs, the fraction of ground and trees in urban canyon. This is an example, a case study for Public Center in London, where we have thermal cameras, and we are able to know the temperature of each specific component in the city. And we know the fraction of walls in each picture, the height of walls, the land surface temperature, and then we can model the heat that is stored in buildings by knowing all these parameters. And for heat storage, we need to know also materials. So we need material-based classification. This is an example of Heraklion, the buildings of Heraklion, and several spectral signatures from very high resolution images. And we perform material-based classifications for the whole city of this type. So we can have information also about the materials and feed our models for calculation of the heat storage. So what is involved with the Supersite? Because we want to transfer the urban fluxes methodology in Athens, and Athens is included in the Supersite, and we have to develop robust monitoring systems for if any of these projects of nature-based solutions will be funded by the European Commission for Athens City to be able to detect changes and to estimate, to evaluate the impact of its nature-based solutions in the city of Athens. And we plan to develop multi-use digital surface models and material-based classifications. So we need very high-resolution data and multispectral and stereo. And for the sites, we have already, thanks to Supersite and to Alexandros, we have already first data set from Pleiades, and we start working with these data sets. And we have the triplets and very high resolution multispectral. And the objective is to have something like this, and we have already started working with this data. Just last week we have started, so I hope that I will be able to present some results in the next workshop of Supersite. So thank you very much. And any questions, please?
Thank you, Dr. Soulakis. Any questions? No? Okay, I would like to thank Forth, also you and Dr. Saris, about providing your research plans. And I know you have received the data from Athens, and Dr. Saris will soon receive in 2017 the data from Pleiades as well for the area of interest. We're looking forward all together for this new cooperation.
very interested to discuss it with applied mathematicians, the new director of the My Institute and its groups, that's very much interested in collaborating with the seismologic community. It's beyond my activities, but since 14 involved in the Supersite, they expressed the interest to other mathematicians. And you always, have to do mathematicians. You never know.
But that's the idea, actually, just to start having people from different disciplines and
PDs and web propagation with more than 20 or 30 years experience on this.
Stefano, would you like to say something?
Yes. Free stereo. Will this be open for the other community? Okay.
Interesting in changes because usually our community considers that the DM, the DSM, and Langabit is something which is static. Maybe with the given economic situation in Greece is static, but not in other cities. But if we have this type of interventions funded by the European Investment Bank or UIA or European Commission, and we have a demonstration project of 15 million euros, you can do some intervention in the city, and then your DSM and the land cover will change. So what is the impact on the heat fluxes from this intervention? What's the impact of the mean ambient temperature and the thermal stress of people? So we try to answer this type of questions, but we need disaggregated data. So this is the common with this community.
Thanks.
Okay, thank you. So I would like to ask Mr. Fabrizio Pacini from Terra 2.
Okay. Yeah. Good afternoon, everybody. I'm Fabrizio Pacini from Terra 2, Italy. I'm here as a project manager of the HESA GeoHazard exploitation platform. So my presentation will try to provide you an overview of the platform capabilities, its current status, and main achievements so far, and some plans. Okay, just to give you some context. So what are the thematic exploitation platform? These are an activity, an R&D activity started by ESA on the EU ground segment to demonstrate the benefits of new technology for large-scale processing of geodata. Despite being technology R&D, however, these platforms are anyway user-driven, and each one focusing on specific thematic areas. In particular, the GeoHazard, I will call it JEP from now on. The JEP design has started already in 2012 during the International Forum on Satellite CO and GeoHazard organized by ESA and Geo in Santorini, and is an enhancement of the precursor Supersite exploitation platform that was designed to support the GeoHazard Supersites and GeoHazard community via the CEO working group on disasters. The JEP is a 27 months contract that started at the end of 2015. It is carried out by an international consortium led by Terra 2 that counts a set of partners both from the scientific and the industrial area. And the underlying concept is based on virtualization and federation of satellite and geodata methods. And the goal is to provide an innovative response to the needs of the GeoHazard community. In a nutshell, what the platform provides is allows the possibility to do on-demand processing for specific user needs, as well as systematic processing to address the need of common information layer for the whole community. It allows massive processing on cloud computing resources to address the challenges of performing monitoring of tectonic areas at the global scale, and also connect to the full Copernicus Sentinel repositories. At the moment, Sentinel-1, 2, and we just started also with the Sentinel-3. And in addition to that, it provides access also to legacy, to more than 70 terabytes of data from legacy mission, ERAS and ENVISAT, and also to specific data collections from other missions such as ALOS-2, Cosmos, ChemEd, TerraSAR-X, that are, let's say, for restricted use because these are provided under special arrangements in the framework of the CEO's working group on disaster and the GSNL. The platform is currently being evolved, so at the mid of 2017 is expected a big upgrade, an important upgrade of the platform with its version 2, but it is already starting and in pre-operation since the beginning of 2016, so since more than 1 year now, and with the active users operating on the platform. So we have inherited from the precursor TEPQueen project a set of 25 users that are, say, active on the platform already from the beginning. In addition to that, the JEP contract includes 6 new partnerships for pilot services. That means that there are new partners that are integrating new services into the platform, and together with this are bringing new users for these services. The partners are listed there. There will be a new set of services that will be made available in the platform, both so mostly INSAR services based on Sentinel-1 data, but we also have a set of optical services, mostly for landslide monitoring and also volcano monitoring. And in addition to that, we have a collaboration with 2 of the ESA disaster risk reduction GSP projects that brings additional, let's say, use case and users onto the platform. In this context, we already have a collaboration with many, let's say, organizations and institutions in Greece. For example, we have among the partners the Corinth Lift Laboratory. We have NOAA, which is active also in one of the 2 GSPs, and will run a trial case on the Santorini volcano area. We have seen before, as we are also supporting the Memphis project. Also IGME will be involved and so on. So there are already many collaborations ongoing that involve Greek actors. So this is just very briefly to give you an overview now. So after the first year of the project, we have already reached a number of 45 users from, let's say, mostly from European countries, but also worldwide, and these are doing different activities linked to volcanoes, earthquake, landslide, and subsidence. It's important to mention that when I say user here, I don't mean a single person, but I mean group of person organizations. So the actual user base is actually much more, let's say, important than what said here. Okay, in principle, we will go on from now until the end of 2017 in onboarding additional users as soon as the platform will be evolved, and the plan is to reach more than 60 users by the end of 2017, so that we will run the actual operation of the platform with an important number of users active. How do we support the user? So we basically foresee 3 main, we call this the platform canonical scenarios. The first one is EUDAT exploitation. This is the simplest one. The more immediate one is the scenario that foresee a user landing on the platform, discovering and selecting data, and using the available processing services to generate and analyze results. I will give you more details later on. Then there is a second scenario that is the new EU service development. This is where we allow user and organization to develop and integrate new services into the platform, deploy them, and make them available either to his group of work or to the whole community. So a new service is developed, integrated into the platform, exploiting the capabilities that we provide and made available for the potentially for the whole community. And then there is the last scenario, that is the new EU product development, that deals with the possibility to generate new information layer, is what we call information as a service. So the case is, for example, a systematic processing of a certain area is carried out to generate information layer that are then stored into the platform and published as a new collection that can then be used for further analysis, for further processing by the community. Going to the scenario one, just to give you an idea of what it is. So what we basically provide, the platform provide a portal that makes available, as you can see from the menu, a large set of data collection. In particular, for the Sentinel missions, we are fully synchronized with the Copernicus Scientific Hub. So we are daily. So we just have a few hours of delay, but we are fully synchronized with the content of the Scientific Hub, and the same is for Sentinel-2 and 3. And then we also provide access to Landsat 8 collection, and as I mentioned before, some, let's say, private collection that are, let's say, made available for in the context of specific arrangement. So basically, the capability this provides is the capability to discover and select data, to download it, and and also there are some tools facilitating the job of the user. For example, we provide the possibility to do interferometric search that makes easy for the user to select interferometric pairs that can be used to feed the available processing services. And also, we already offer a set of processing services that have been integrated in the platform that range from the most known one as Gamma, the Sentinel Toolbox, Diapason, and so on, but also could include new services that are developed by partners of the platform. There is a very simple way to interact with these services for the user. So by clicking on the icon, it gets access to the service interface, and by simply drag and dropping the selected geodata into the interface, can then start the processing, monitor the progress of the processing, visualize the results, download them directly, and also make them available to the community if wanted. This is not, let's say, mandatory, but there is the possibility to make the results of processing as public, so that can be visible and shared with the community. Then there is the second scenario I was mentioning before. Very briefly, this is accomplished through let's say an integrated environment, a cloud environment that provides the user with a working sandbox where he finds a set of tools that allows to easily interact with the platform in terms of data access, accessing the catalog, and so on, to do some tests in this, let's say, somehow closed and controlled environment, and when ready, to deploy it and make this public to the community or to his colleagues. And the service will be then available through the interface that I showed just a few seconds ago. Last scenario is the new product development. As I was mentioning, the case here is, for example, one of the relevant cases that we have in the platform is the integration of an insert browse processing service from DLR that has been integrated already in year 2017, that is processing. So during 2016, we have mapped daily the whole European tectonic area, producing for each, let's say, Sentinel-1 pair falling in that area, 6 layers of information from the interferometric phase, coherence, amplitude change, and so on. And all these are continuously, systematically processed every day and made available to the user. For example, at the moment, we are doing a ramp up from the European tectonic area to the global tectonic area. This will be done gradually, but at the moment we are already processing about 95 pairs per day, and the ramp up will lead us by mid 2017 to reach more than 150 pairs per day, and at the end of the year we should reach the full amount that is about 260 per day. This is a very challenging task, but we find this really great, and the results are very much appreciated on the platform. Again, so to stay on services, just to show the evolution that we had in terms of service offer. We have started at the end of 2015 with just a few conventional insert services, including the Amazon TopSAR, the insert browse, and one service that was this bus that was running on GPod and invoked by the JEP. And during this first year of the project, we have integrated a new set of processing services, both systematic and on demand. We have also, as I was mentioning before, an important set of optical services working with Sentinel-2 and Landsat-8 data, and we expect during 2017 to further enlarge this set of services by adding a new one, so that at the end the offer will be really consistent and impressive. And also it's important to mention that we have services developed by scientific institutions, but also by industrial company. For example, we will have soon the FastVel terrain motion velocity map service from TRA Altamira, that is a partner of the consortium. Okay, just another point, very brief, is that the platform also foster collaboration in the community, leveraging on social media to promote results. We have a Twitter channel that continuously pushes information about the availability of new data and results. We have a blog where users are free to post and to have discussion about results or item of interest and so on. And also important to mention that, of course, for accessing the platform in its full capabilities, users need to be, let's say, accepted by ESA, because at the moment ESA is the sponsor of the platform. But we also foresee at the moment the possibility to give free access for visitors. So with this free access, the user gets access just to a reduced set of capabilities, but is able to at least to have an idea what's going on. Okay. Just a few examples of achievements. I take just a few minutes. I think one important example was the work that we have done for the seismic pilot led by ESA and NGV that was activated for the earthquake in central Italy on last August. In that case, the JEP had been, let's say, selected as one of the repositories to access, exploit, share data and result. So several collections, several data sets related to the event were made available on the platform. Processing with several processing services were carried out. So on the Amatrice area with the Amazon, this one from Terra 2, this one from INGV, with different resampling periods. Also, we started the high resolution service for a period of time to monitor the evolution of the, let's say, of the event in the area. And all these results were collected, made available in a community area, and the access was made easy and immediate for the user. For example, just clicking on a button from the JEP carousel. We have posted blogs. We have posted information on the blog about the availability of data and so on. So this was, in our opinion, a really success case of the use of the JEP in the management of, let's say, the activities after an important event such as the one of the Central Italy earthquake. Just to conclude, another important point is the collaboration between JEP and EVOS. JEP has been selected as the gateway for the satellite data thematic core services in EVOS, so it will be an integral part of EVOS. Will host EVOSAR, that is one of the main services of EVOS. This is very important also in terms of future sustainability of the platform, because this gives us a visibility of the future even after the end of the current contract that will be the beginning of year 2018. That's okay. Okay.
So I will start with a question. Should we consider that for the case of, for example, of the Enceladus Hellenic Supersite, it will be available to our community to have access to the portal and upload data and use the different modules, or even upload our own modules and use the platform just to produce some products?
Yeah. Okay. Yes. So in principle, yes. So as I was mentioning before, currently we have this JEP early adopters program that still has some, let's say, seats available, but this is subject to let's say, a process where it is at the moment the European Space Agency, at least during 2017, that let's say makes the final decision of whether to get on board or not the user. This because, of course, giving this kind of access requires some, also doing the processing has some cost in terms of support, resources, and so on. And so until ISESA, the let's say the founder, then they take the final decision. From what I can say, I think there is openness in doing that, so I would encourage this. Okay.
Thank you very much. Any questions? Okay, let's start.
You presented us a very sophisticated procedural platform for elaborating data and presenting data. And behind all science that we do, the scientists, it should be some practical applications. So my question is the following. Did you gain any information before the August earthquake in Amatrice? Second, did you get any, based on this experience, bad luck with the 300 victims, did you get any alert or any kind of information about the stronger event of October? Did you see any information which you could use for the protection of the people, or just only science?
So the difficult question for me. So please consider that I'm not, let's say, a scientist. We don't. So as a JEP, at the moment we provide the capabilities of the platform. Then the, let's say, scientific investigation is left to the scientists, to the user. So I mean, it is more. Of course, I don't know. We of course we open access to INGV for doing some. So then it's INGV that has the mandate and
Yes, but do you know any kind of applied research that contribute? Did you have in your idea? Okay, you provide the data.
Yeah.
But do you have any information about the results of research which made use of your data for the benefit of the society?
So actually not yet. At least with the direct results. So I cannot say that. So I have seen results, but then I cannot say if they really had already found this kind of results.
Okay, thank you.
To question a more general one, the beginning, have you developed any synergies between your TP with urban TP led by DLR, Thomas S. and Mattia Macocini, these guys?
With DLR?
With urban TP, geohazard TP with urban.
Okay, with urban. So it's not, there is at the moment, the only, let's say, synergy. So for me, it's a bit difficult to answer because as Terra 2, we are involved in both the types. So we are, as a, let's say, as a company, we are involved in both. The answering with my, let's say, JEP hat, the only synergy that we have developed is that now we are going to publish in the JEP the global urban footprint, because it was requested by some users to have this, because it can be useful in some cases to have the possibility to cross, let's say, check the INSAR data with the ones from the global urban footprint. This is, let's say, the first, let's say, synergy we established with the urban tab. But I think the reason for not going further, also for not being further, is that there is a different level of maturity of the platform. For example, the urban tab is still in a earlier phase with respect to the geohazard, but we expect that in the future, as soon as they complete the development, there will be much more possibilities.
And I have a technical one, not for SAR, but for Sentinel-2. May I?
Yes.
Because you have also, the question is if you have integrated Send2Core in your cloud, because in my lab, our experience so far is to work with Google Earth Engine. I have great experience on this, but the problem is that if we need to correct the time series of Sentinel-2, we have to work offline.
No. Yeah, we have integrated the Send2Core. We have it. It is available in the sandbox for. Is it available in two ways? In the sandbox, if you want to develop a service by using the Send2Core, and also as a service if you want to use it, let's say, as an end user. So yes, the answer is yes.
Thank you.
Thank you, Fabrizio. I have a question. To me, it's clear that what you are developing is the platform, okay, for the processing, distributed processing of the data. But my question is, what is the level? What is how much of what you presented today about ZEP is operational? I mean, what is the extent that this platform can be used by users, remote users, for processing data?
Well,
thanks.
Yes. So yes, actually, it depends. It depends on the service. So we have, as I've shown before, we have several services that are being offered. Some of them are in a quite mature stage. For example, so just to give an example, we have Diapason that is available almost since the beginning. We have an agreement with CNES and Altamira for the maintenance of it. So it's quite stable. So I would say, so if you would ask me, can I use Diapason for doing processing? I think its measure is really operational. Then there are some services that have been integrated at the beginning of the project through, let's say, in-kind contribution from external parties that now aren't part anymore of the consortium. And for them, let's say, the maintenance is a bit more difficult for us. So these services are a bit less stable. We as a, let's say, platform operators don't have in-depth knowledge of these services. So indeed, we are now in a process of, let's say, separating the services. There will be a set of services that will be published as really operational. Some other will be published as kind of best effort because they are from open source initiatives and so on. So we are in the process of doing this, but there is a good part of the platform that I would say, I cannot say operational, because you know that in principle I cannot say this word for an ESA platform like the TAP, but let's say pre-operational for sure.
Okay, I'll make it more specific.
Yes.
All right. Can I run S-bus with 150 pairs of DRS or MVSAT?
Currently, S-bus is not directly on the platform. It is a GPod service that we access remotely. Okay.
Okay. And what is on JEP platform actually? If I want to run the ferrometric processing only diapason?
No. So you have diapason, you have stamps. You know that you have stamps. You have now the new Sentinel-1 bus from CNR that works, but it works on Sentinel-1 data. We have the Snap Sentinel-1 Snap interferometric processor. We have the insert browse. So we have quite some services. Then there are some optical ones.
Okay, thank you, Professor Parharidis.
Hi, Fabrizio. Just I want to give an information that we're going to organize a workshop of 2 days at the end of March about the JEP in our university, because many of our students are involved as validators in the JEP. So there is this possibility. I pass this information also to Alexandros in order to be published through the Supersite. So young people can come there here, learn about the JEP, and then have a hands-on or snap, etc. Okay, thank you.
Okay, thank you.
Thank you very much.
Let me just give you just very short information. It's just for because it may be of interest that we have started since let's say a few weeks systematic processing over the Corinth Rift area with the DLR high resolution insert browse service. So I mean this can be of some interest for.
Okay, thank you. Yeah, for sure. So we move to the next presentation is from Mr. Manesis.
Good afternoon to all from me as well. I'm Charis Manesis. Okay, thanks. From Geosys Amelas, and this presentation is about a multi-sensor example in the framework of the implementation of Indesmusa project. Indesmusa was an R&D project that was focusing on the installation and configuration of an innovative multi-sensor network towards the formation and seismic monitoring of urban subsidence-prone areas, and eventually the dissemination of all this kind of information that is coming from the network through the development of a WebGIS platform in order to support the end user. The study area is Kalohori region, which is located in the northern part of Greece, and more specifically in the western part of Thessaloniki. And it's selected because of its unique characteristics, as it constitutes an urban, industrial, and critical infrastructure area that has suffered a lot in the past from severe soil deformation and earthquake phenomena. So the business problem was the soil deformation in urban, industrial, and critical infrastructure areas. And the key requirements towards this kind of problems, it was the appropriate installation of the instrumentation in order to create a multi-sensor network, the online monitoring of all this kind of information, the development of the appropriate methodologies, and especially different technological domain methodologies, and the support of the scientific staff of the project, and the dissemination of the results and the visualization of them through the WebGIS platform in order to serve the community and the end users. So we had to develop a seamless solution so as we can support quick response from the appropriate users. Just a few words about the funding authorities and the participants. The project was implemented under the framework of Greek-China bilateral collaboration, and it was funded by General Secretariat of Research and Technology. From the Greek side, the participants were Geosystem Hellas as the commercial partner, which was also the coordinator of the project, along with the Institute of Engineering Seismology and Earthquake Engineering, and the Institute of Geodynamics of National Observatory of Athens. From the Chinese part, iSpatial was the main commercial partner, and the study area was Shanghai. In this slide, we can see the study area, and with the different polygons, we can define the different subzones of the study area, which was consisted of free field, gas and oil tank area, urban village area, and the industrial area. We can also see with different colors the exact installation points of the accelerometers, 7 in total, 2 Leica GPS GNSS base stations, 2 water level sensors, 1 radar tide gauge that was installed in the port of Thessaloniki, and with the bigger orange polygon, we can see the total area that we used for 3 time series from 3 flights. And in order to map the area with different sensors, we used DMC RGB near infrared and aerial imagery sensor, and 1 LiDAR sensor in order to map the area. And we also used 2 time series Gold View 2 imagery dataset. So with this kind of information, we managed to create a 4D temporal data approach. Our approach is, we can see it in this slide, with the use of the mobile GNSS network, the water levels, the tide gauge, and the airborne and LiDAR dataset, we managed to monitor the soil deformation. With the use of the base GNSS stations and the accelerometers, we managed to monitor the earthquake motion in structure and soil. And with the use of the airborne and LiDAR dataset and the accelerometers, we managed to create the 3D city model, so as we can investigate the soil and structures interactions. Here we can see some photos from the permanent installation in the steady area. In this slide, we should thank the municipality of Delta, as long as the Hellenic Petroleum Enterprise, for the kind actions and help during the installations and their availability during the whole project lifetime. In this slide, we can see some measurements for the implementation of the project in order to map the soil subsidence. With the blue dots, we can see the water level measurement points of the drillings. And with the red dots, we can see the GNSS stations. And now a few words about the flights and the equipment that were appropriate for the flights. We used, the first flight took place on the 2nd of May of 2014, and we used an ALS-60 LiDAR sensor of Leica, and 2 other flights, one in the May of 2014 and one in the May of 2014, in order to produce the digital air imagery photos with the use of the ZI DMC RGB near infrared sensors. Additionally, as I said before, we used two time series data of worldview to acquisitions. In order to support the time series measurements, we had a very dense and dispersed ground control points network, as we can see in the map. And we are very glad because we managed to fuse both the real and digital worlds in order to deliver dynamic data and reliable and actionable information in order to support the end users. And we are very glad to say that we supported the whole information lifecycle from the moment of capturing the information to the process of the raw data, to the further process in order to make them available through internet, and finally to the delivery to the end users. As for the use of 3D city models towards risk and vulnerability of urban sites, as I said before, we managed to create a 3D city model with the use of the ALS 60 LiDAR dataset and the database of the town planning sim. So we created a very sophisticated 3D repository of the buildings and the other constructions that are placed in the area. And generally, regarding the 3D city models, they do help towards risk and vulnerability of urban sites to natural hazards, as they constitute an inherently spatial problem. They do help against risk management, disaster preparedness, and future urban planning. And they do help in other technological domains as well, such as banking and real estate, as they can be further used in order to evaluate and re-evaluate land values, for example. And these unique datasets clearly are a motivation for investments and their future plans. So as I said before, we did develop a WebGIS platform in order to disseminate all the information that was coming from the implementation of the project. Here we can see the general architecture of this kind of application. On the left side, we can see the data layer that consisted of raster, LiDAR, vector, and non-geospatial data. On the main part, we can see the application layer, which is based on the development of ERDAS Apollo software, and it is the core system of the WebGIS platform. So we connected this kind of applications with our data, and we managed to catalog and furtherly process the data and create the appropriate OGC services so as they can be available through internet applications. And finally, in the right part, we can see the presentation layer, which is the final user interface of our applications, where the end users interact and can visualize the data. Here is the user interface of our application. In the main part, we can see the map panel, where all the information is visualized. The end users are provided different interactive tools so as they can navigate in the map, such as zoom in, zoom out, pan, get info, etc., etc. On the left side, we can see the layers that are visualized in the panel, in the map panel, and there are also different tabs providing the end user the possibility to make extra queries and search for additional data and visualize them in the map. And of course, different tools are provided to the end users, such as measurement tools, providing third-party services, authentication, etc., etc. Of course, there is also the possibility for 3D visualization in our application, which helped us a lot because we managed to provide the 3D city model to the end users. Different other characteristics, it's the data access to the recordings of our multi-sensor networks. very essential for this kind of applications. For example, all the instrumentations are digitized and geo-referenced, and they are accompanied with their additional data, and their recordings are linked to their attributes, so as the end user can just double-click on an instrument of interest and get the relevant recordings. The end users can create and make multi-purpose and multi-criteria queries on the data, so as they can find the data they want. For example, they can search via spatial search, or they can search via, let's say, type of data set or metadata. And of course, attribute-based search. For example, in this example, we can see that the end user is looking for an earthquake event, stating that he wants magnitude over an exact value and depth below an exact value. So when he applies for the search, the system just visualizes the results. Of course, there are also linked all the reports that have come from the scientific, let's say, integration and scientific job of our partners are linked to the relevant events. For example, earthquake reports are linked to the exact earthquake events, and they are available to the end users. The end users have access to online data catalog. There is also possibility of 3D measurements and 3D analysis in a 3D visualization mode. The users can also visualize third-party data services in the forms of WMS or WFS and relevant OGC services. And it has online on-the-fly styling capabilities. So we should also note that we did participated in the EO Open Science 2016 that took place in the ESA premises in Frascati, and Ms. Karalabopoulou chaired the server session. We should point out that in this session, a lot of similar applications were demonstrated, and the main message is that the user is a challenge, and every application should have in mind that they should serve the tools improvement and the end users interaction and the ideas for the business model, since all platforms should be alive and used for the benefit of the EU society and citizens. So I would like to end my presentations with some beautiful photos of the study area, and I'd like to say some special thanks to Mr. Marios Papanikolaou for them. Thank you very much for your attention.
Any questions for Mr. Manesis? No, okay. We move on with the next presentation for Mr. Bolanos from Planetech Hellas. What is ringing?
I brought some help because my throat hasn't been very much collaborative the last couple of weeks. Good evening, everyone. I'd like, first of all, to thank Mr. Savvaidis for the initiative, and of course all the participating of the in the Supersite. I think it will help in bring value not only to the participants, to the members of it, but also to society, I believe, very much. My presentation today will not be, of course, scientifically oriented. We are in Planetech a provider of solutions. We try to think providers of technology, but mostly solutions. We like to think. I will speak to you about Reticus. Reticus is our platform through which we try to provide geoinformation as a service, which is the late trend worldwide, I would say. So in very few words, Reticus is a cloud-based platform that uses as input, of course, satellite data, but also any type of, also many other types of open data. It is continuously updated, and through a subscription, which is also the innovative aspect that we try to think that we change the general business model of geoinformation nowadays. It provides indicators, maps, and reports more than the data itself that the final users, I am not very sure that is very much interested. Reticus offers for the moment 4 categories of services. First is the displacement. Second is the marine. Of course, I will go further. I will discuss in detail the displacement that is relative to my today's presentation, which I tried to make it specific in critical infrastructure monitoring. So second is the marine domain. Third is mostly the wildfire, but in general the land, I would call it. And the second and the last and fourth one is the urban dynamics. If you try to divide these 4 categories that I just mentioned in specific services, talking about displacement, of course, landslide subsidence, infrastructure stability at a monthly basis and even more frequent, based on the visibility, on the revisit of the satellite data that every time are used in order to get the information. As far as marine is concerned, seawater monitoring, algae bloom, fishing areas related EO services, these at a daily basis. Type of services, of course, are offered in our platform. The third one, land, covers the land cover, wildfire, illegal crops, soil sealing, even at a weekly basis time frame. And the fourth category of services offered through our Reticus platform by subscription is urban dynamics, which consists in urban change, infrastructure building, and urban heat island. This is the being a service offered in the cloud. This is the web page which anyone can log in and have access to this different information. I will just play right now a video that that should start, yeah, by this. This is the website where anyone can join, and as I mentioned before, by subscription can have access to what we want to bring to the user, specifically for the service related to the subscription, to the service related to the displacement, is for any specific area in the world that the user is interested, to be able to have its PS, the permanent scatters points that are an outcome of an activity implemented in Planetech together with our connected company GAP. GAP is a spin-off of the University of Bari that has implemented this SPINUA algorithm, this SPINUA called algorithm, that is a permanent scatter interferometry algorithm that we in Planetech integrated within our platform and brought to the wider public in this cloud infrastructure. You, of course, are very much aware of where this technique has application. And I will just go through the rest of the presentation by showcasing some examples that we have worked. This, for example, is related to the monitoring of public works. In this specific case, ANAS, that is the operator of the road network in Italy, has used the service in order to identify optimal paths for the road, avoiding landslide areas. In this case, you can see where with the red, the points can showcase areas that are affected by a landslide, or that are not affected but are have an increased risk, increased relative risk. Another example is used by a municipality in Sicily for urban areas monitoring. And I'm just showcasing in this picture a specific specific displacement in a short period. In this case, in December 2015, where for some reason there was this displacement of a specific point. Regarding spatial planning, in this case, we have the analysis made in the region of Venice in Italy, where in order to create and update the territorial management plan, the reticus was used to provide the displacement service to the relative authority. This is another relative example where an area is showcased in where you see on the right of the slide the areas where they have a significant risk, where movement has been detected. One other important example that we very much like to showcase is for the operator of the water operator in Milan, where they use the subscription of the service in order to detect leaks. So by monitoring the network of the water and the sewage network, where displacements of the ground are found, they can lead to the identification of certain leaks in the water or sewage network. Of course, for construction sites, monitoring construction site is another example. Mining areas monitoring, definitely. This is in another activation of the service relatively to subsidence inducted by mining activities. One other is, of course, is the activation that we did in order to monitor the dam of Mosul in Iraq, where the service was activated where our reticus was activated in order to provide the monitoring of the dam of Mosul, where as it seems that there also for this specific case some movement has been identified. I will just go very quickly with the other services also, just by mentioning them, with just taking the opportunity in the last 2 minutes that I've left. The marine service is relative mostly to the water quality. This is an example from the area of of Ionian Sea, where we monitor chlorophyll concentration, sea surface temperature, and water transparency. The wildfires, as I mentioned, and I will just play here a short video that is showcasing based on Hexagon geospatial on the Hexagon geospatial suite the burned area mapping in an automated enough procedure that we have integrated in our Reticus. So in this example, is showcased the before and after the fire area. And the urban dynamics, which mostly for the moment is relative to soil loss calculation. As I mentioned before, with indexes and diagrams, that is a user-friendly, we think, or we try to make it as user-friendly as possible. It is calculated relative to urban dynamics, the way that the ground is and the soil is the consumption of soil in time is moving forward. I will just close by the example of Amatrice, the unfortunate event that there was in Italy some last year, where also here an automatic procedure that was based on before and after the event satellite image can categorize in 5 different categories, from completely destroyed, highly damaged, moderately damaged, and negligible to slight damage, or and last category, not affected. The area where that was hit by the earthquake. If I can summarize, Reticus is a service that can be monthly updated, provides continuous monitoring. We try to make it as much as possible easy and ready to use the dynamic information that we provide. As I said, again, globally available, and it can be at the base of many more smart maps that can be built upon it. And with this, I would thank you very much for your attention.
Thank you, Mr. Balano. That was a very nice presentation. Any questions? We have a minute for questions. Okay, we look forward for cooperating with you in the future.
Very much.
Yeah. Thank you. So I would like to ask Dr. Condoes to provide his presentation. You will follow up with the presentation of Dr. Balassis as well.
Yes.
So it will be one thing, all in one.
Thank you very much. Hello, everybody. I'm Haris Kondoes. I'm Research Director of the National Observatory of Athens. Thank you very much for your kind attendance. I'm the last presenter. I will try to be very brief. And thanks also, Alexandros, for kindly inviting me to give you a presentation about the Beyond Center of Excellence and the Enigma geomagnetic array, which is led by one of my colleagues, George Balasis. Okay, I will start with the Beyond Center of Excellence. Of course, when I arrived here, I have to tell you that some colleague asked me, is NOAA part of the Supersite? I don't know exactly what this means. I don't know what exactly means if NOAA it is, but but in any case, I think that if it is in, or if it is not in, I don't know.
It has been invited, we can say that, isn't it?
It will be, in any case, a good opportunity I think, for the Greek Supersite initiative and for NOAA to collaborate and especially to rely upon the space capacities that are provided through the Institute of Space Applications and Remote Sensing of the National Observatory of Athens. Yes, I belong into that institute. I have the responsibility of leading this Beyond Center of Excellence. This is a European Space Center of Excellence for the which use the Earth observation technology for the monitoring and the mapping of natural disasters in Southeastern Europe, in the wider Mediterranean. It has expanded its activity in North Africa, Middle East, and the Balkans. And now, through the involvement of the Beyond Center of Excellence into the Copernicus EMS activity, actually it serves several places and several activations all over the world. It is to be said that the Beyond Center of Excellence is built upon antagonistic money, so it has used completely money that comes from competitive programs. It costed to the European Commission 2.5 mega euros for the development of the Center of Excellence. It hosts space infrastructure and monitoring capacities of 1.5 mega euros, and since then all the operation of the Beyond Center of Excellence is self-sustained. It actually uses competitive money. It's not using at all state money, and it keeps its operations, daily operations, through antagonistic programs of the European Commission, of the European Space Agency, and other funding organizations through antagonistic calls. Okay, this is the Beyond, and today my presentation, it's about a very brief overview of the center and the partnerships that it has established all over the world. I'll speak, I think this is the interesting of this meeting today, about the ground segments which are operated by the center and which can be of the benefit of the Supersite initiative to use it and facilitate the access to the data. And at the end, I will give you a short presentation about our geohazard services, the so-called GeoHAD system of services, and the Hellenic geomagnetic array, as I just mentioned. Okay, this is a conceptual diagram of our center. In the middle of the center, there are there are three actually pillars of services relating to different hazards, to meteorological and human-induced hazards, to atmospheric hazards, and also to geophysical hazards or geohazards. And of course, in order to serve these different cases, or let's say derive services which are useful for the decision makers so as to handle these specific cases of hazards, what we do is that we have established the so-called capacity building node. The capacity building node is an integration of data, of space data, of in situ data, of expert know-how, and of course processes, chains, and models in order to exploit the data and provide the new information which is used by the decision makers for the management of the disasters. And this is another diagram which shows exactly what is the ecosystem of services, products, infrastructures, and models, of course, that are used by our center. On the left side, you see with the orange circles to be presented actually the different capacities, the monitoring capacities. We are operating several monitoring acquisition stations for satellite data, reception of satellite data, also in situ monitoring networks. In the middle, there is a big library of modules of data fusion techniques, of data processing, algorithms, data processing chains, and algorithms that are fully dedicated for the delivery, for the exploitation of the data and the delivery of specific downstream services as they are specified according to the very, very specific user needs. Most of the services that we are providing are based upon the long-term consultation with the end users and providing them so as to fit exactly to their needs. So most of the operational services have a past of long studying, research development, and once we deliver a service, it's actually what is the outcome of the research that meets exactly the specific need of users. Of course, at the same time, the research continues and the services are continuously enhanced at the pre-operational level. And of course, to the right side, you see an ecosystem of services. There are system of services. It's not system of services like FireHub, for example. There is a series of services relating to the monitoring and the management of fire disaster in real time, as well as in the preparedness and recovery phase. Flood Hub is the same, relating to flooding hazards. The Atmo Hub, relating to the atmospheric disturbances. GeoHub, of course, which is something that I will emphasize today, present you several or showcasing several examples of this GeoHub system of services. And of course, different services which are mainly provided for the needs of the Copernicus Emergency Management Service relating to preparedness and risk and recovery pillar of Copernicus CMS, receiving activations for risk and recovery for many different places over Europe and over the world. Of course, we are not alone. Okay, it's obvious that we cannot do all this by ourselves. Only, of course, we are collaborating with many different organizations over Europe and US. Of course, we are collaborating with space agencies like European Space Agency or DLR or Italian Space Agency, but also research organizations, universities, and operational organizations as meteorological services and civil protection authorities all around Europe. I said already that we serve the Copernicus program. I'm sure that you know, most of you know the Copernicus. There's no need to say more, but Copernicus is the big flagship space program of the European Commission, and in Copernicus we are developing space systems, services, and integration of in situ data. And what beyond that actually is the support of the EMS pillar of Copernicus, the pillar which is providing services for the management of disasters in real time, as well as providing services related to the preparedness phase and to the risk and recovery phase. So here actually is what we do on a monthly basis. Almost we receive one activation through the framework program that we have signed with the Copernicus CMS. What these activation programs are, the civil protection authorities are asking us to provide with risk and recovery services for the management of many different disasters, not only geohazards, but also meteorological disasters, atmospheric disturbances, air pollution phenomena, and so on. Beyond is not noting that is part and member of the ESA's Geohazard Lab initiative. This is very new. In the last year, 2 years before, we were a user of the so-called SEOS seismic pilot activity of ESA. Now, in a new, let's say, agreement with ESA, we became partner of the ESA's Geohazard Lab initiative, which runs in the SEOS working group on disasters. Other members are ESA, of course, NASA, CNES, ASI, DLR, and JAXA. Our role there is to facilitate the access to the satellite data, and this is part of part of my presentation today, but also to facilitate the access of the users into the distributed platforms like JEP, as it was presented before by Dr. Fabrizio Faccini, and generate timely advanced tectonic products, especially for the seismic and volcanic seismic pilot and volcanic pilot. And through this activity, we provide the background support to the Supersite initiative. Here you see the priority areas that are in SEOS, in seismic pilot and SEOS volcanic pilot activity. So these are the areas where priority in the reception of data and processing of data is given by the SEOS working group on disasters. And last but not least, the center is providing support to the institutional authorities through specific, very specific MOUs that have been signed with the Civil Protection and Emergency Authorities of Greece. Here I mentioned a few of them. The Fire Brigade Authority, we're providing real-time data for every 5 minutes, actually, in the Fire Brigade control room for the management of fire disaster over Greece. The General Directorate of Rehabilitation in Greece, we are providing early warning, but also at the same time assessment of damages due to hazards in different cases of hazards over Greece. The General Directorate of Forest and Natural Ecosystem Protection, and many different forestry services and local authorities that are asking us to provide support in cases of several cases of hazards, not only fires, but also earthquake, toxic cloud dispersion, dust circulation, and so on. Okay, in regards to our ground segment, we operate a region-wide XNL band acquisition station. This provides real-time access to a multitude of satellite data. I mean, the EOS Aqua and Terra, the well-known MODIS. Most of us, I think, we have used MODIS data. SOMI, NPP, VIRS data, JPSS, NOAA, VHRR, METOP, FENGU. All are these data that are acquired over Europe, North Africa, Middle East, and the Balkans in real time. And they are data that are in visible infrared and thermal infrared. So it is data that may be useful for several geohazard activities, like the ones that the Greek Supersite at the same time is dealing with. We are operating 2 MSG acquisition antennas of DVBS and DVBS2 systems. I mean, they have proven very useful in cases like the example presented before my colleague Nektarios Chrysoulakis for urban islands, thermal heat waves over urban areas. My colleague Ifigenia Keramitsoglu is doing also a lot. It's providing a lot of services, also for the civil protection, but also for the local authorities using this type of data. This is also data which are delivered, received and processed and delivered on a 5 minutes basis. And I think I'm sure that most of you know about our activity concerning the operation of the first collaborative data hub for the reception and redistribution of Sentinel data. You may remember that Greece was the first signing the agreement with European Space Agency for establishing and operating this collaborative data hub. This was a rather successful operation, which is in full operation today. About 110 gigabytes of Sentinel data are downloaded on a daily basis by third parties, by users actually, who are accessing our collaborative data hub on a daily basis. Today we deliver Sentinel-1, Sentinel-2, and very soon Sentinel-3 and Sentinel-5P data. And again, the area which is covered by the collaborative data hub, the Greek mirror site, is North Africa, Middle East, Southeastern Europe, and the Balkans. Okay, this shows a bit what is this architecture. You know that the Sentinels are acquired through acquisition antennas, which are operated by European Space Agency. They are located in specific scientific sites over the world. And the data from the antennas are directed to the processing and archiving facility centers. There they get some to up to specific level of processing, and they are directed to two nodes. The node 1, which is the T system, which receives Sentinel-A1, but now Sentinel-2 as well, and the node 2, which is the OVH node that receives again Sentinel-1 and Sentinel-2 data. And here is what exactly this architecture is, and where we are placed. The core segment is this central part of this architecture. And the users, there are several hubs around this core segment. The scientific hub, it's the one that it is used by every single user over the world, but here the access to the data is done through web. So many times, if there is a big circulation of data or many users asking for data, this scientific hub may be stuck. There is the collaborative hub. This is the Greek mirror site, which has a direct link to the core ground segment with a very fast optical line. And this is the benefit of using this hub, because there is a fast line that is delivering data from the rolling archive of ESA. And of course, there are two other hubs, the International Hub and the Copernicus Hub, which are not open to the wide public, but they are there for publishing data to the space agencies all over the world, and also to the projects of the Copernicus program. And of course, I don't this is just to show you that our transfer rate of data is about 28 megabytes per second, which means that you can download the data, an image of 10 gigabytes in about 4 to 5 minutes. And this, I think, is the big benefit of accessing to the collaborative data hub for accessing to Sentinel data than using the scientific hub. But of course, all the hubs are there, and they are for the use of the users, of the scientists, and the community. And this is something that I announced for the first time, because this is very new, and I'm very glad to say that a week ago we kicked off a new project, an agreement with European Space Agency that uplifted our ground segment from collaborative data hub to the core ground segment. That means that for the next 4 plus 3, 7 years, a collaboration scheme which comes to be the NOAA, the GRNet, Greek partner of Giant, the Serco company, and a small part Airbus, we will operate all the data hubs of Sentinel data, including scientific hub, international hub, Copernicus hub, and collaborative hub. And in 3 months from now, we should have in full operation the international hub, and in 2017, the whole activity, the operation of all hubs, it will be also available. And I think, okay, this is useful to say, and this is a diagram showing where is our place in that architecture, what we call integrated ground segment of Copernicus data. So you see these are PDGs, which means the ground segment, the acquisition antennas, the two nodes that they host directly data from the antennas, and the operators of the data hubs, which is NOAA, Serco, and GRNet SA. GRNet providing high-performance computer and data centers. No, I don't know if I have time. It seems I don't have time to speak about the GeoHub, unfortunately. But anyway, very, very briefly, the GeoHub is a system of services which receives data from the mirror site and the acquisition antennas on a systematic basis. The data are stored, and according to the type of service and the type of information we want to provide, the data are retrieved and the appropriate processing chains are invoked so as to provide data like interferometric SAR deformation, maps, co-seismic slips, sleep assessments, and so on. There are many different applications that have run already, starting from the old Athens earthquake up to the most recent earthquakes that have happened in Greece and in many different places of Europe. Most of them have been of these studies have been part of scientific publications in well-known scientific journals. Here you see several of the examples that have been produced by the Beyond Center of Excellence, actually by the GeoHub system of services. This is another interesting example. This was done in collaboration with INGV, with my friend Stefano here, and it was the Kefalonia earthquake. Actually, we as part of the geosseismic pilot activity, we received Cosmos climate and TerraSARIX data, and we produced the co-seismic slip, and from that, all the geometry related to the fault geometry actually related to the earthquake. Other examples, the Central Italy history of rupture from August 24 to October 30th of last year. Another publication that it is under evaluation. The Santorini volcano during the unrest period 2011-2012. Dr. Stefoli before presented the collaboration with Beyond, the surface subsidence in Volos and in other places. In Kalohori, the Kalohori area has been part of another publication, and many different activations for risk and recovery as they have been awarded to us by the Copernicus CMS program. Activations in Azores, in Madeira, in Austria, in Bulgaria, and so on and so on and so on. So I'm sorry I don't have much time, as I can understand. I see the chairman here.
Yeah, use the time that they provide you. It's a matter of ability also. You have to exercise this. I think you have so many slides. It was amazing to do that in 10 minutes.
But because big, sorry, I promised to George Balassis to say very few about the Enigma, because Enigma is is collaborating with the Beyond Center of Excellence. Enigma is a geomagnetic array. Okay. It measures the geomagnetic field of the Earth. There are 3 stations in Greece. They are part of the Supermag network. This is a worldwide network. About 300 stations exist today. Here you see the network, the Supermag network, and of course the Enigma is one of the reasons of having hosted Enigma in our activity is our attempt to try to see if perturbations in the geomagnetic field may be related as precursor phenomena to seismic hazards. Anyway, I think it's better to stop here. Thank you very much for your kind attendance, and of course, to my ability, I can reply to any questions, if any.
Thank you very much. Thank you. I have just the first question. I will start with Enigma. How many stations it is now on Enigma?
3.
3 in Greece or 3?
3 in Greece.
Okay. So, sorry, any other questions from the audience to Dr. Cordoes? Yeah, Fabrizio.
Just a quick information. This Greek National Hub, does it provide global coverage or just the, let's say, Mediterranean area and part of Southeast?
Okay, there are 2 things. The Collaborative Data Hub covers the North Africa, Middle East, Balkans, and Southeastern Europe. Okay. The other activity, as part of the core segment, covers over all the world, all hubs.
Okay. Anyway, access to, let's say, access to users will be through the first one, right, or not? So,
access of the users too.
So from as a user or as an Exceller user, the access will always remain through the collaborative.
From the Collaborative Data Hub, you get direct access as user to that area of interest, which is Europe, actually. Europe and North Africa, etc. As a user of the scientific hub, any other collaborative hub which is supported by us, you can access data from every part of the world.
Professor Bahar.
Thank you, Harris, for your presentation. I have just I need a clarification. It's very interesting, this Geohazard Lab initiative. Do you know if it already exists? Is it just at the discussion?
if it exists, the geohazard.
Lab initiative.
The lab initiative is currently discussed with ESA. It is, as I told you, yes, as I told you, is
something under discussion.
Yes, it's under development. There is a proposal from ESA about this, and comes as let's say as an outcome of what has been done before in the so-called geoseismic platform. Maybe Stefano could provide some more information on that, but this is the evolution, let's say, of what was done in the last year.
Because I am member of the group that talking about this initiative, and that I know that we are in the phase of discussion yet. We don't finish still the discussion. It's true, Stefano? Yes, it's under discussion. So it's very interesting initiative, but it's under discussion still. Our group is involved in this discussion.
Perfect, that's good.
Actually, there are groups involved in the discussion.
Okay, thank you. I would like to thank you, Harris, for this nice presentation. So I would like to thank you all, first of all, for having the time and the patience until this time of the day, like 7:30, to be with us. I would like to thank all the presenters. I will provide a few bullets of what I can say was the most important things discussed today. One is that it seems that especially for the Enceladus Greek supersite area, there are a lot of different data, both in situ, already existing satellite imagery that has been used by different groups, which is very good, so that there is experience in both cases, both on satellite imagery and also in situ data. There's been a lot of work being published. We have seen that there are different platforms that are available to provide either data or services like GEP, we have seen from Fabrizio, from TerraDue. And the most important of all, it seems that there is a big interest from all of us here and from people that were here earlier today, just to find a way to work more on our collaboration through the Enceladus Greek Supersite, so that we come up with best profit of all this information, prepare new research results that will help for disaster risk reduction. I would like to thank Stefano Salvi for being here with us. Stefano has been very helpful all the time, and here also being with us today. If there are anything that you would like to come up on a discussion, yes, Christos.
It is the first supersite in Greece, so the title
Supersite
is very correct.
Yeah, for the central Greece, I think the Enceladus includes also both Corinth, Ionian Sea, and Evoikos. It is written on the full title. In my presentation, it was written also Evoikos. In my presentation today.
Yeah, today was the first time I met it.
Yeah, okay, that's wait, and that is something. Yeah, you can reply, Stefan. I mean, that was something that we were asked from the GeoSAC to move on. So we use another name so that because that's happening also in other areas of the world. But maybe Stefano, you would like to. You mentioned it earlier, but you can comment. I think, Stefan, I think Christos maybe would like to reference to the discussion we had when we started this initiative, and we had a long discussion with a lot of different parties involved, also the National Observatory of Athens, that what will be the Greek supersite area. And at that time, we decided the Greek supersite area, that will be just the area we have now in our plan. So from at that time, for our idea about it, it didn't seem that that might be another area. So Greece is, this is the area with the most earthquake activity. And
well, you know, Santorini could be.
If there was someone who would like to present something more than what has been presented, then it could. That's the case. We are here to listen about it. I mean, there have been invitations to everybody, so I'm expecting that based on the research plans we have, at least from the two of the parties that have sent to me, I mean, from Forth, there are discussion about working with seismicity and how to check stress levels with both INSAR and also earthquake activity in the area. That is something that has been discussed already. So thank you very much, everybody. I would like to welcome you for a drink outside.